Inside, there was some liquid water and an electrolyzer. With the external power supply, the electrolyzer could operate, splitting the liquid water into hydrogen and oxygen, which would then be stored separately. Chen Yu closely monitored the data from thousands of sensors on the space laboratory. Suddenly, one sensor sent a signal to him via the communication antenna. Its status had changed in the previous moment, indicating that it had detected the generation of electricity. Chen Yu's spirits lifted. It really worked. Electricity was being generated in the plasma ring. Next, he needed to observe the rate of electricity generation to see if it met theoretical predictions and whether it was engineering feasible. If the output was too low to even cover the energy consumption for the spacecraft's round trip, it would naturally be deemed unfeasible, even if the electricity generated was sufficient. If the surplus was excessive, it would still not hold much value from an engineering perspective. Chen Yu remained focused, cautiously testing, calculating, and waiting. Gradually, an hour passed. He had collected enough data and entered it into the computational model, instantly yielding the final result. In that moment, Chen Yu was stunned. The calculated result was far beyond his expectations, leaving him pleasantly surprised. The power generation efficiency of the plasma ring here is astonishing, to the point that it leaves Chen Yu in disbelief. Even considering the current efficiency of the space laboratory, the overall engineering efficiency reaches as high as 4,563. In other words, with 1 unit of energy invested, Chen Yu can obtain 4,563 units of energy in return. This is nearly 5 times the profit. Moreover, this space laboratory is only experimental in nature, and its efficiency is not particularly high. If Chen Yu were to create specialized power extraction equipment and scale it up, thereby reducing losses through mass production, the expected returns could potentially reach 10 times, or even more. Fantastic. I knew it, Chen Yu silently exclaimed. With this in mind, there was nothing more to discuss. He immediately abandoned the other plans and began to push forward with this one with full force. The primary task of this plan is to build a specialized power extraction station at the plasma ring around Jupiter. It must be large enough to extract power with high efficiency and equipped with sufficient electrolyzers to store ample water, as well as liquid hydrogen and liquid oxygen. Under Chen Yu's direct command, the design blueprint for the first power extraction station quickly passed self-inspection and entered the production phase. Meanwhile, specialized robots for the plasma ring also began production, along with supporting electrolyzers, power extractors, specialized steel, and dedicated transport spacecraft. The scene on one of Jupiter's moons was bustling with activity. The minerals and energy from various parts of the moon were transformed into components, robots, and spacecraft under Chen Yu's operation. The first batch of 10 modified transport spacecraft set sail, carrying the corresponding components and robots to the plasma ring. Subsequently, self-powered robots in the zero-gravity environment began to extract these components and directly assembled them in space. Then came the second batch, third batch, 9 batches in total, with 156 spacecraft arriving, allowing Chen Yu to finally assemble this massive structure, which measures 100 meters in length, 56 meters in width, and 11 meters in height. It resembled an insect with over 20 pairs of wings, soaring majestically through the vastness of space. Those 20-plus pairs, totaling more than 40 wing-like structures, are all high-performance plasma ring power extractors. Through the interaction with the materials at the plasma ring, a continuous supply of electricity is generated and transported into a cylindrical inner space. At this moment, the first power extraction station has been completed. All components and systems have been debugged and are ready to begin production. So let's get started. Hundreds of thousands of kilometers away, at Chen Yu's command, the first power extraction station vibrated slightly, officially beginning the journey of harnessing energy from the plasma ring. A substantial amount of electrical current was generated from the power extractors, with thousands of electrolyzers inside starting to work simultaneously, producing hydrogen and oxygen that were collected along different pipelines and stored in the warehouse for natural cooling, ultimately transforming into liquid hydrogen and liquid oxygen. An improved model of the transport spacecraft was already waiting here. After some time, its 2 warehouses were filled with liquid hydrogen and liquid oxygen, and it set sail towards a moon of a gas giant. On this moon, an ice-based solid oxygen power station had been upgraded in advance into a hydrogen-oxygen power station. The arrival of this spacecraft brought the most important fuel, allowing the combustion chamber to finally ignite, releasing immense heat to boil water, which in turn powered the generators. Ultimately, a continuous supply of electricity was produced, feeding into the vast power grid constructed by the project leader, driving machinery, trains, and factories. The first power station's engineering trial was a complete success. The project leader looked at the many operational power stations and felt a surge of ambition. Construction of the second power station commenced. Chapter 29. Standards. The newly completed first power station still had a certain experimental nature, so the project leader was cautious not to make it too large. After all, This involved many areas previously unencountered, and rushing into it could lead to problems. A steady, incremental approach was the key. Throughout the construction of the first power station, the project leader accumulated valuable experience and developed many improvement ideas. Consequently, the conditions for building the second power station were now mature. In terms of power generation capacity, the first power station had a total installed capacity of 150,000 kilowatt-hours, meaning it could generate 150,000 units of electricity per hour. However, this was the level at the plasma ring. Transporting it to the moon involved significant losses. The 150,000 units of electricity could electrolyze about 3 tons of water, producing approximately 0.33 tons of hydrogen gas and 667 tons of oxygen. Upon reaching the moon, this liquid hydrogen and liquid oxygen would burn again to convert into electricity, with additional losses. Based on the current efficiency, about 800 units of electricity could be generated. Thus, the 150,000 units at the plasma ring would shrink to about half when applied to the project leader's industrial facilities on the moon. After accounting for transport losses, only about 30 would remain. However, this was unavoidable. Electrolyzing water was currently the only available energy storage method for the project leader, as other methods lacked engineering feasibility. The only hopeful alternative was a type of energy storage called flywheel energy storage. Simply put, it converts electrical energy into kinetic energy by accelerating a rotor to extremely high speeds in a vacuum environment. However, this technology was too advanced, and the energy storage flywheel currently produced by the project leader was less efficient than hydrogen-oxygen storage, leaving it to be applied only when technology advanced further. As for battery storage, that was even less feasible. Batteries had limited capacity, were too heavy, and could not match hydrogen-oxygen storage. Nevertheless, even with a final efficiency of only 30, the project leader felt no disappointment. There was no way around it. The resources from the gas giant were essentially limitless, and one could never exhaust them. Moreover, a power station was essentially a one-time investment that would provide long-term benefits. So what if the efficiency was low? Building more would solve the issue. The project leader lacked nothing but engineering capacity. As a result, the construction of the second power station, which has a total installed capacity 10 times that of the first power station, was immediately initiated. At the plasma ring, it can generate an average of 160,000 kilowatt-hours per hour, and its technology is more advanced, with total losses lower than those of the first power station. Once transported to the fifth moon of Jupiter, it can leave behind approximately 32 units, meaning that the fifth moon can receive about 12 million kilowatt-hours of electricity supply per hour, amounting to 5 billion kilowatt-hours annually. Furthermore, while achieving an installed capacity 10 times that of the first power station, the volume of the second power station increased by less than 4 times. At this moment, the total annual electricity consumption of the 5th and 14th moons under Chunyu's name has reached 1 trillion kilowatt-hours and continues to grow rapidly at an average rate of 6 per year. Based on this consumption level, Chunyu needs to construct a total of 300 power stations equivalent to the efficiency of the second power station at a growth rate of 134 stations per year. This figure would be an unimaginable number for humanity at its peak, but it is completely inconsequential for Chunyu. For him, building factories in space or on the planet's surface makes little difference, especially since the 5th and 14th moons are small, making rocket and spacecraft launches very convenient. A factory at the level of the second power station would only be considered small on the planet's surface, with many factories that are 10 or even 100 times larger. When constructing the third power station, based on the previously accumulated engineering experience and the maturity of power station construction technology, along with improvements made during this period, the third power station was directly enhanced to 10 times the level of the second power station, while its volume increased by less than 3 times. After reaching the third station, the rate of efficiency improvement began to slow down. The performance of the fourth station only reached 12 times that of the third, with its volume reduced to 0.8 times. The fifth station saw some improvement, but less than before. After experiencing significant early-stage advancements, the power station technology mastered by Chunyu entered a phase of slow, iterative improvement. By the time the sixth power station was constructed, the technology had finally matured and stabilized, making it difficult to achieve further significant enhancements in a short time. Thus, Chunyu standardized the design and began mass production based on the sixth power station as the template. The newly standardized power station has an installed capacity of 250,000 kilowatt-hours at the plasma ring, and after accounting for all losses, the effective energy retention when delivered to the 5th or 14th moon reaches 36, meaning that one power station can provide approximately 9 billion kilowatt-hours of electricity per year for Chunyu. With about 300 of these stations, he can cover all his electricity consumption. While gradually reducing the installed capacity of the oxygen generation stations, the number of hydrogen-oxygen generation stations began to grow rapidly. In the 10th year after the standard power station was finalized, 30 of the oxygen generation stations were replaced. At this moment, an average of up to 70,000 tons of hydrogen and up to 200,000 tons of oxygen were directly extracted from the two moons to supplement the supply sent from the plasma ring to the 5th and 14th moons, along with up to 680,000 tons of water being delivered to the plasma ring. The spacecraft responsible for transporting hydrogen, oxygen, and water has reached a total of 600. These 600 heavy transport ships shuttle tirelessly between the plasma ring and two planets. In the skies of these two planets, the tail flames of the transport ships shine like bright stars, illuminating almost the entire planet, creating a spectacular sight. Qinyu's industrial facilities operate day and night, supported by energy from the plasma ring. Fortunately, the technical requirements for these 600 spacecraft are not high. Essentially, they just need an engine and a large empty shell. Otherwise, if Qinyu, who could not even build a true interstellar spaceship, would never have been able to create such a seemingly massive fleet. Sometimes, Qinyu marvels at his own capabilities. Because of these 600 spacecraft, along with the power stations at the plasma ring, numerous robots, countless factories, and numerous trains and machinery, all have come from his own hands and are completely under his control. Reflecting on the days when he had only one robot after just landing on one of the moons, Qinyu feels as if it were a lifetime ago. However, it is not yet time for complacency. Qinyu reminds himself, my technological level is still too low. I can't even build a basic fission power station, let alone fusion. Otherwise, why would I need to exert such effort to draw power from the plasma ring? I need to work harder and strive to advance technology more quickly. Chapter 30. Electromagnetic Cannon. With a continuous supply of energy from the plasma ring, Qinyu's pressure was immediately greatly reduced. In the following time, Qinyu continued to construct numerous power stations, aiming to reduce the consumption of local energy to below 10 of total consumption within 10 years, and ultimately reduce it to 0 at the right time, completely solving the energy shortage problem. However, at this point, Qinyu discovered a new issue. Due to the limitations of his technological level, the interstellar transport ships carrying energy transfer demands had too high a failure rate. Even though Qinyu had simplified their design as much as possible, essentially just a remote control system, an engine, and a cargo hold, the failure rate was still too high. This not only consumed a large amount of Qinyu's computing power, but when failures increased, it severely disrupted energy supply planning. On several occasions, Qinyu even had to limit the electricity consumption of certain factories. With only about 30 units of energy supply currently, the number of heavy transport ships shuttling between the plasma ring and the moons exceeds 600. When the supply reaches 100, won't the number of transport ships soar to 2,000? And with the increasing energy demands each year, could it reach 2,500 ships or even more? The thought of needing 2,500 ships to transport energy day and night one day makes Qinyu's head ache. It is impossible to improve the performance of the ships in the short term. Therefore, an alternative space transportation solution that is highly reliable, low in energy consumption, and low in computing power requirements must be sought, allowing him to avoid allocating too much attention. Qinyu thought for a long time and gradually consulted the knowledge base, and suddenly had a bright idea. Electromagnetic catapult technology? This seems applicable to interstellar transport. Without hesitation, he immediately set to work on engineering verification. The principle of electromagnetic catapult technology is quite simple. It essentially involves using electromagnetic acceleration to launch a payload, fundamentally converting electrical energy into kinetic energy. Research related to this technology existed during the Earth era, primarily applied in military contexts, such as electromagnetic cannons. Qinyu planned to build an electromagnetic catapult directly at the plasma ring, loading liquid hydrogen and liquid oxygen into metal boxes, and then directly launching these boxes to one of the moons of Jupiter. He considered reducing the launch speed to around 40 meters per second. This way, after selecting an appropriate trajectory, the metal boxes would enter orbit around the moon upon arrival. They could then autonomously transport themselves to the surface of the celestial body. The same method could be used for transporting water ice to the plasma ring. First, he would build a similar electromagnetic catapult in orbit around the moon, transport the water ice to that orbit, and then launch it directly to the plasma ring using the catapult. This approach would eliminate the need to construct and operate numerous spacecraft, significantly saving computing power and energy. The only drawback was that to ensure the metal boxes could directly enter orbit, the speed had to be maintained at around 40 meters per second. At this speed, it would take over 2 months to travel from the plasma ring to the moon, which was somewhat lengthy. However, it didn't matter. As long as the first one arrived, subsequent deliveries would follow continuously, ensuring an uninterrupted energy supply. At this moment, The first electromagnetic catapult had been completed at the plasma ring. Under Chun Yu's remote command, a metal container, approximately the size of a standard container on Earth, with an internal space of about 25 cubic meters and loaded with liquid oxygen, weighing around 285 tons, was positioned at the launch end of the catapult. With a massive supply of electricity, the electromagnetic force acted on the metal container, gradually accelerating it. At the moment it left the cannon, its speed reached 426 meters per second, and it began its slow journey toward the moon according to a preset trajectory. Chun Yu collected all the data generated from this launch for detailed analysis. After more than 2 months of a long journey, the container successfully reached the vicinity of the moon. The moon's gravitational pull affected it, altering its trajectory and drawing it closer. The metal container successfully entered orbit. Chun Yu immediately launched a rocket, shaped like a table, into space, which then attached itself to the container. The rocket ignited, slowing the container down, and gradually dragged it to the surface of the moon, landing perfectly in an open area in front of a hydrogen-oxygen power station. The first trial was a complete success. During this period, Chun Yu conducted the second, third, and up to the 16th experiment, launching a total of 16 containers. With each experiment, the efficiency improved slightly. After 16 trials, Chun Yu believed he had mastered the technology. So, it was time to start mass production. Chun Yu was incredibly excited. The following month, the first batch of 100 standard electromagnetic cannons was assembled at the plasma ring. Its appearance resembled a thin tube inserted into a cube adorned with wings. These wings served as power extraction devices, providing energy for the electromagnetic cannon, while the cube was equipped with thrusters to offer stability through counterthrust. Additionally, there was enough space reserved for docking spacecraft and temporarily storing containers for filling. At this moment, numerous fast-travel spacecraft were retrieving the hydrogen and oxygen that had been ionized from various power extraction devices and delivering them to the electromagnetic cannon. After unloading, the internal machinery of the electromagnetic cannon immediately filled the containers with these liquid hydrogen and liquid oxygen. The containers were then placed at the launch end of the cannon and ejected, with one container being launched. At the current efficiency, the electromagnetic cannon could launch a container every 10 minutes, with each container holding 285 tons of liquid oxygen or liquid hydrogen. Thus, in one day, a total of 144 containers could be launched, equating to a total mass of 100 tons, which meant that 100 electromagnetic cannons could launch 410,000 tons daily. Meanwhile, the number of heavy interstellar transport ships had reached 700, but they only transported an average of 320,000 tons of liquid hydrogen and liquid oxygen per day. Based on these figures, Chun Yu determined that he only needed to build a total of 260 electromagnetic cannons at the plasma ring to fully meet the existing energy demands. In reality, even fewer cannons would suffice. The reason was simple. This method was more energy efficient than ship transportation. Chapter 31. Moving after detailed calculations. Chun Yu found that once the electromagnetic cannon launching technology was applied on a large scale, the energy retention rate could increase from the previous 36 to nearly 47. This would further reduce the demand for liquid hydrogen and liquid oxygen, meaning Chun Yu could stockpile more fuel reserves for emergencies. Chun Yu once again embarked on a furious construction process. He completed the construction of 260 electromagnetic cannons at the plasma ring in less than a year. Consequently, of the more than 700 spacecraft, only a small portion was converted into maintenance vessels, while the rest were retired. The construction materials were recycled, significantly alleviating the shortage of steel supplies. With an average daily supply reaching 1 million tons, nearly 350,000 containers of fuel, Chun Yu had completely resolved the concerns regarding energy shortages. He redirected his focus back to scientific research. At this moment, the year had reached 200 in the new calendar. On the 200th anniversary of the arrival at the fifth moon of Jupiter, Chun Yu looked back, filled with emotion. It has been 200 years, a full 200 years. Compared to the past, the changes on this moon have been revolutionary. The entire planet has been developed, and almost every place bears the traces of human presence. The massive emissions of gases over these 200 years have even given this small celestial body a macro-level atmosphere capable of affecting lighter materials like certain plastics, which can be slightly moved by the wind. Of course, the air here remains quite thin and is not breathable for any form of life. It is mostly industrial waste gas, containing a large amount of toxic substances like sulfur dioxide, ammonia, and chlorine gas. At this moment, reflecting on the past and looking to the future, Chun Yu feels increasingly invigorated, because at this time, he has finally advanced his chip technology to a point just 10 years shy of peak human capability. He is now capable of small-scale production of chips using a 7-nanometer process. It's worth noting that the central computer of the spacecraft he is currently aboard uses a 7-nanometer chip. Once he can manufacture 7-nanometer chips, it will mean he can independently construct a supercomputer on par with the spacecraft. Moreover, this supercomputer can discard the complex reliability redundancies of the central computer and eliminate many constraints, allowing for a larger design without concern for energy consumption. All these factors combined mean that this new supercomputer will bring at least a 50-fold increase in computing power. God knows how long Chunyu has been troubled by insufficient computing power. To solve this problem, he even had to establish a technologically backward supercomputing center and grant permissions to lower-tier chips, leading to a significant rise in overall error rates, causing great resource waste, and preventing him from fully advancing technological development. Now, all these issues can be resolved once the new supercomputer is built and has sufficient computing power. It's time to prepare for relocating. Chunyu is once again embarking on large-scale construction. He plans to set up his new home underground on this moon. There, not only are the cooling conditions better, but the thick rock layers can also shield against external radiation and high-energy charged particles, as well as protect against asteroid impacts. Of course, Chunyu will not place all his hopes on this alone. He plans to install thousands of small electromagnetic cannons around this new supercomputer to ensure that no external threats can approach. The working principle of these small electromagnetic cannons is similar to those at the plasma ring, except that the projectiles have been changed from containers to bullets, and the launch speed has been significantly increased. The specially designed projectiles launched by the electromagnetic cannons can weigh up to 10 grams and reach speeds of up to 26 kilometers per second, giving each projectile an energy of 38 million joules, which is slightly more powerful than the most potent anti-tank sniper rifles from the previous era. Assuming a small asteroid unexpectedly targeted the location of the supercomputer where Chunyu resides, over 600 electromagnetic cannons would be directed at it under the guidance of satellites and radar, firing projectiles at a rate of over 200 rounds per second. Even a large iron ball would be pulverized. Therefore, ensuring the security of his location is of utmost importance. To protect this supercomputer, Chunyu constructed 3 hydrogen-oxygen power stations, each capable of meeting the entire power demand. Under normal circumstances, they operate at 1/3 of their capacity, but can instantly ramp up to full power if any of the other stations encounter issues. In addition, Chunyu prepared 6 sets of uninterrupted power supplies buried deep underground in various locations, each capable of sustaining low-power operation for 12 hours, ensuring he can wait for the power stations to restore electricity. Furthermore, whether it is the fire protection system, cooling system, maintenance system, or safety redundancies, Chunyu implemented the highest standards. This effectively alleviated any concerns. The supercomputer utilizes over 100,000 of the most advanced chips that Chunyu can manufacture, complemented by a specialized data distribution system. For any computational task, he can efficiently distribute the workload across all the chips simultaneously and easily aggregate the results from them. Together, they form Chunyu's brain. After spending a full year on its construction, Chunyu finally completed it. Following hundreds of remote self-checks to confirm everything was functioning correctly, he specially connected it to the central computer of the spacecraft via a network cable. Through this wired connection, Chunyu accomplished this move. Arriving at his new home, he felt a sense of exhilaration, like a dragon entering the sea or a tiger entering the jungle. Previously, while still inside the spacecraft, it felt as though he was a dragon forced to squeeze into an earthworm's hole. With just a thought, immense computing power surged forth, solving several extremely complex mathematical problems in less than 2 milliseconds. Chunyu extended this vast computing power to every endpoint of his industrial facilities. In that moment, all previously delegated permissions were revoked. Instantly, the coordination of the robots became seamless again, and the precision of the assembly line operations improved, eliminating various errors and unreasonable discrepancies. Even so, Chunyu's computing load level only reached 10. Finally, there was enough computing power to develop new technologies and theories, advancing technological progress. Chapter 32. Migration. At this moment, in the hundreds of research centers that had been completed but remained vacant, the experimental robots finally began to show signs of activity. In the chemistry laboratory, robotic arms retrieved various reagents and began operations within a fume hood. In the materials lab, a computed tomography microscope started scanning the fracture of metal materials, attempting to process metals under various smelting and casting conditions. In the propulsion laboratory, various high-performance chemical propellants ignited violently, leaving a long-tail flame behind the experimental equipment. In the electromagnetic acceleration lab, coils stretching several kilometers were powered on, with projectiles moving at high speeds within. A dedicated supercomputing center handled the computational tasks generated by these laboratories. The final calculations were input to Chunyu, who began further induction, organization, analysis, association, and speculation, tasks that only he could accomplish. Yu's scientific research model is quite similar to that of scientists on Earth. Scientists there also utilize supercomputers for preliminary data collection, organization, and analysis, further processing the final results. However, Yu single-handedly replaced thousands of scientists, capable of processing numerous scientific categories and experimental data alone. Under these circumstances, the original Mu-Ba-type spacecraft was gradually phased out, and Yu finally produced the newly upgraded Mu-Geo-type spacecraft. Previously, he had constructed many interstellar transport vessels, which differed significantly from the initial Mu-Ba-type spacecraft. Ultimately, those vessels were merely improved versions of the Mu-Ba-type and could not be considered a brand new generation. At this moment, the updated engine layout of the Mu-Geo-type spacecraft enhanced fuel efficiency, restructured the overall design, and upgraded material performance, qualifying it as a new generation of spacecraft. It is important to note that what Yu refers to as Mu-Ba-type and Mu-Geo-type spacecraft actually encompasses a series of engine processes, material technologies, and structural layouts. Any spacecraft built based on this technical framework, regardless of appearance or specific purpose, whether interstellar transport vessels or communication rescue ships, are collectively referred to as Mu-Ba-type or Mu-Geo-type. Currently, compared to the Mu-Ba-type, the Mu-Geo-type spacecraft possesses significantly more powerful performance. Its radiation resistance is better, stability is enhanced, thrust is greater, and speed is faster. However, Yu still feels somewhat dissatisfied. Up until now, all the spacecraft I have built are still within the civilian category. They are far from being practical military warships. Civilian and military are two completely different realms. For instance, the latest Mu-Geo-type spacecraft can achieve a maximum acceleration of only 0.6 meters per second squared. This acceleration is sufficient for civilian use, but in military applications, it would be absurd. It's almost slower than a snail. Its armor is also quite thin, measuring less than 2 centimeters, easily penetrated by a bullet. While its performance meets civilian standards, it is dismal when assessed by military criteria. Nonetheless, Yu has always been clear about one goal. After the mysterious destruction of Earth and his inexplicable fusion with a computer, it is foreseeable that there are undoubtedly many unknown and mysterious entities in the universe. In the future, I will inevitably come into contact with them. Only powerful warships and thousands of heavily armed combat spacecraft can serve as my only bargaining chip for self-preservation. In the future, I must build combat spacecraft. Compared to my grand aspirations, the current M9 class ship seems a bit lacking. The journey must be taken step by step. I comforted myself, saying, one day I will be able to construct a real warship. However, with the M9 class ship now in hand, I can start to pursue certain endeavors. This is a significant undertaking, one that holds as much importance for me as the landing on the small moon of a giant planet over 200 years ago. I plan to relocate my base to one of the moons of the giant planet. After more than 200 years of continuous development and extraction, the small moons of the giant planet have shown signs of resource depletion. There is no way around it. They are simply too small to support my dreams. At this moment, I have completed the initial accumulation of technology and possess a certain level of industrial strength. Therefore, moving to a larger celestial body to continue rapid development in a broader environment has become a necessity. The second moon of the giant planet is a suitable choice. The giant planet has 4 large moons, known as the Galilean moons. All other moons are relatively insignificant compared to these 4. Among them, the second moon is the smallest. Even so, its diameter reaches about 100 kilometers, with a mass over 50,000 times that of the small moon I previously occupied. One can imagine how many minerals, resources, and energy are stored on it. Of course, in terms of mass, size, and resources, the other 3 Galilean moons are larger and have more abundant reserves. However, the second moon has an unmatched advantage over the other 3. In addition to having a large amount of water, it has been detected to contain numerous vast methane lakes. And it also possesses an atmosphere primarily composed of oxygen. Although this atmosphere is extremely thin, I can find ways to enrich it. After enrichment, by directly mixing it with methane for combustion, I can obtain a continuous energy supply. At that point, I won't have to exert effort to extract energy from the plasma ring. I had previously launched many satellites to it, conducting detailed surveys of its terrain and measuring various data. I observed that the entire surface of the second moon is almost entirely covered by a thick layer of ice, with the thickest parts reaching over 100 kilometers. Many crucial mineral elements are sealed within these ice layers, making extraction relatively convenient. Scientists from the era of Earth theorized that beneath this thick ice layer, there should be an ocean of liquid water, where life might even exist. Of course, the people of that time had no means to verify this. However, since I have now decided to continue my development on the second moon, I must find a way to verify this possibility. Studying these elements is crucial for Yu to enhance his understanding of the universe itself, the origins of life, and evolutionary patterns. At this moment, a Wood 9-type spacecraft, acting as a vanguard, had departed from one of the moons, loaded with research equipment, and was rapidly heading towards another moon. Chapter 33. Methane lakes. The distance between the two moons is quite significant, at its closest being about 500,000 kilometers, and at its farthest exceeding 1 million kilometers. This Wood 9 research vessel was traveling towards its destination at a maximum speed of 28 kilometers per second, taking a full 6 days to finally slow down and reach its side, beginning the attempt to land on the surface. The latest model of the Wood 9 spacecraft is equipped with the capability to take off and land on the surface of large moons with atmospheres. The engines emitted fierce flames, gradually reducing the speed of the research vessel. However, even so, the intense friction with the atmosphere caused the outer shell to endure temperatures of several hundred degrees Celsius. It was only after the speed decreased to a certain level that these high temperatures dissipated. The spacecraft slowly landed, with the intense tail flames scorching the thick ice layer on the surface, creating a large amount of water vapor. Moments later, this vapor condensed due to the extremely low temperatures, transforming into snowflakes that slowly fell. In the future, such launching and landing spacecraft would need to be fixed to designated locations. Otherwise, the surface would have to melt and freeze each time, which would be too troublesome. Chenyu pondered this. With several seconds of communication delay, Chenyu carefully operated the hatch of the research vessel, allowing several reliable robots inside to slowly walk out. What lay before Chenyu was a true ice and snow world. The entire moon was almost covered by a thick layer of ice. The ground was ice. The mountains were ice, the valleys were ice, and the basins were ice. Everything was ice. Everywhere was ice. However, this place was not as pure and crystalline as the fairy tale descriptions of ice and snow worlds. This is the Jupiter system. Above the moon, a massive pale yellow planet gazed quietly down. Nearby, a bright, somewhat blinding star illuminated the area. These were Jupiter and the Sun together. These two celestial bodies provided lighting conditions comparable to those of Earth's twilight for this side of the moon. The ice and snow beneath Chenyu's feet were not at all crystalline and transparent, but instead mixed with a large number of impurities, appearing dark and dirty. In some areas, there were also green, red, blue, and other colors, making it look even more chaotic. The overall scene presented a picture of a dark, dirty land stretching out under a dim sky, extending to an unseen distance, lacking any sense of beauty. However, for Chenyu, this was a positive sign. The disorder and dirtiness indicated that a significant quantity and variety of minerals were stored within these ice layers. Only in this way could it support his industrial development. If it were a scene of crystal clarity and beauty, it would indeed be pleasing to the eye, but it would also mean that there was nothing but water ice, which would be disastrous. The reliable robot moved quickly and arrived at a peculiar place after about an hour's journey. This was a lake composed of liquid water, shrouded in a mist that made it appear almost otherworldly. It was astonishing that liquid water could exist in such a location with temperatures dropping to minus 160 degrees Celsius. However, this phenomenon can be fully explained by scientific theories. The moon is gravitationally locked to its planet, always showing the same face. The immense gravitational pull from the planet tugs at the moon's core, resulting in frequent and intense geological activity that leads to continuous volcanic eruptions, bringing a significant amount of heat from the core to the surface. This ongoing heating creates conditions for the existence of liquid water on the surface. Chenyu maneuvered the robot to the edge of the lake and took some measurements, discovering that the water temperature was just below 10 degrees. It couldn't be any higher. Although the moon has an atmosphere, it is too thin. If the temperature rises even slightly, the water would boil away into the atmosphere. Only water that is above freezing but not too warm can exist in liquid form. After examining the area, the reliable robot continued on. After a while, it stopped again, revealing another lake ahead. This lake exhibited a reddish-brown color, quietly resting on the surface of the moon, appearing like a gem from above. A gentle breeze stirred the surface, creating faint ripples that were barely noticeable unless one looked closely. This was methane. Methane, the primary component of natural gas, has a high calorific value, making it suitable for power generation. Although this lake appeared small, it had an average depth of about 6 meters and covered a total area of 26 square kilometers. This small methane lake stored roughly 6.5 million tons of methane. There were countless similar small methane lakes on the moon, with many larger ones as well. At that moment, seeing the methane lake and determining its composition allowed Chenyu to fully relax, filling him with genuine joy. With oxygen in the atmosphere, a methane lake, and a total water reserve greater than that of Earth, along with numerous mineral resources, this place felt like paradise. However, entering paradise also has its thresholds. After over 200 years of development, Chenyu finally qualified to establish a base on such a large moon. Once the situation on the moon was confirmed, large-scale migration efforts immediately commenced. Numerous new spacecraft transported Chun-Yu's extensive industrial facilities to predetermined locations on the moon. Factory after factory began to rise. First was the power plant. These plants were built next to the methane lake, drawing liquid methane as if it were water into the pre-processing workshops, while simultaneously using air compressors to compress the oxygen-rich atmosphere of the moon, also sending it to the pre-processing workshops. After preliminary processing, the two gases were sent into the combustion chamber to begin burning. Immediately, the supercritical unit generated a large amount of electrical energy, which was then transmitted through high-voltage lines to nearby factories. Mines also rose rapidly. Chun-Yu treated the ice layer of one of the moons as a mineral layer to excavate, extract, and refine. Massive amounts of ore were continuously smelted into metals and alloys, ultimately sent to factories for further processing. Railways crisscrossed above the ice layer, and heavy trucks raced everywhere. In the sky, there were also low-pressure helicopters specially developed by Chun-Yu, roaring as they flew around. In just 10 years, the industrial level on this moon had reached the sum of that of 2 other moons. This level was already at its limit on those smaller satellites due to their size, which could not support further development. However, on this moon, such an industrial level was just beginning. Chapter 34. Uranium mine with the industrial level on this moon meeting the standards. It was no longer appropriate to stay on another moon and continue to remotely control operations here. It was time to move once again. During this period, Chun-Yu further improved his chip technology, upgrading from a 7-nanometer process to a 5-nanometer one. This meant that he could integrate more circuits on the same sized wafer, thereby achieving higher performance and greater computing power. At the same time, a new generation of supercomputer operating system was completed. Using this operating system, Chun-Yu could reduce overhead from interrupt requests and inter-process communication, and made significant performance improvements in areas such as vectorization, program loops, memory hierarchy, and data locality optimization. The new operating system, more aligned with Chun-Yu's own existence, allowed him to operate the underlying hardware more conveniently and coordinate the collaboration of hundreds of thousands of chips to achieve his goals. Combined with more advanced chip manufacturing technology, this brought Chun-Yu a computing power increase of up to 20 times. At this moment, Chun-Yu transferred himself back to the spaceship and then landed next to the newly constructed supercomputer base on the moon. He then transferred himself inside through a wired connection. At this moment, a surge of computing power flowed in. Chun-Yu controlled industrial facilities comparable to the combined capacity of 2 moons and felt completely at ease. His computing power usage was only at 0.12. The increasingly abundant computing power provided Chun-Yu with greater confidence. He immediately made arrangements for the upcoming development plans. The first was to continue expanding the industrial foundation, iterating towards higher precision and performance. Second, Chun-Yu planned to undertake something he had never dared to do before: developing fundamental physics. Fundamental physics is the foundation of all technology. Until now, Chun-Yu could be said to be relying on the legacy of human civilization. All the technologies used by Chun-Yu have developed from the human era. While they may appear innovative in form, they lack any true innovation in essence. Without fundamental physics and new physical theories, how can there be innovation? Researching fundamental physics requires significant investment, yields slow results, and consumes vast resources. This has been the fundamental reason why Chun-Yu had previously refrained from delving into fundamental physics research. However, the situation is different now. At the peak of human advancement, their technology had only just reached the capability of manned missions to Mars. My future, however, is destined to soar through this vast universe. It is time for me to drive the development of science myself, Chun-Yu thought. He planned the first batch of fundamental physics research facilities and listed them out. At the top of the list were 10 space telescopes. These 10 telescopes cover every band of electromagnetic waves, from radio waves and microwaves to infrared, ultraviolet, visible light, X-rays, and gamma rays. These space telescopes will become Chun-Yu's eyes to gaze into the depths of the universe. In addition to the space telescopes, Chun-Yu also intended to build 2 gravitational wave detectors. However, the technology for these devices is too advanced and may not be feasible to create just yet. He planned to accumulate the necessary technology over time. Furthermore, there are neutrino detectors and, most importantly, a high-energy particle collider. To uncover the mysteries of the microscopic universe, particles must be subjected to extremely high energy levels to reveal their internal secrets. A particle collider is such a device. It can accelerate microscopic particle beams to nearly the speed of light, allowing them to collide with instantaneous energy densities capable of generating miniature black holes. Of course, this is something only the largest particle colliders can achieve, which humanity at its peak could not accomplish. Chun-Yu merely proposed a plan, intending to gradually realize it later. However, if a large collider cannot be built, Starting with a smaller one to make do is also acceptable. After all, Chen Yu's own database does not contain cutting-edge scientific data. He must conduct collision experiments repeatedly to master this data. The third development plan is equally important. Although there is an abundance of methane and oxygen on Europa as energy sources, Chen Yu is still dissatisfied. He has decided to pursue higher energy acquisition methods. After all, while methane and oxygen are plentiful on Europa, what about spacecraft traveling through space? They cannot refuel after every short distance traveled, can they? While it may be manageable within the solar system, what will happen during interstellar travel? More efficient energy acquisition methods are the only viable solution. The human era has already proven that energy from nuclear fission and fusion, derived from within atoms, is the most effective and practical. The original atomic bomb was developed based on nuclear fission energy. The even more powerful hydrogen bomb is based on nuclear fusion energy. Humanity had mastered controllable nuclear fission and built numerous nuclear power plants, but controllable nuclear fusion remained unattainable until their demise. Chen Yu naturally did not have control over this, but he had already realized that if he wanted to roam freely within the solar system, not to mention beyond it, controllable nuclear fusion was the only feasible energy acquisition method. Only by mastering controllable nuclear fusion could a truly functional combat spacecraft be built. Chen Yu was clearly aware of this. Therefore, while continuing large-scale construction and expanding his industrial scale, numerous fundamental research facilities and nuclear industry laboratories were also put into construction. To master nuclear energy, the first thing to do was to find fissile materials. On Earth, people typically used uranium-235 or plutonium-239 as fissile materials. On Europa, after exploration by Chen Yu, plutonium-239 was not found, but 2 uranium mines were discovered. There was a lake made of liquid water. The highly radioactive uranium heated the water ice here, allowing it to remain in liquid form despite the inability to access Europa's geothermal energy. Now, what Chen Yu needed to do was to separate uranium-235 from this water. Let's build a centrifuge factory, Chen Yu thought. Thus, a power station rose from the ground here. Next to the power station, an even larger factory slowly appeared. This factory housed thousands of centrifuges, each capable of spinning at extremely high speeds. With thousands of centrifuges spinning rapidly together, along with other equipment, the power consumption of this factory exceeded that of an entire city from the previous era. Chapter 35. Nuclear power station. Uranium existed in this lake in the form of uranium oxide, commonly known as yellowcake. Yellowcake is insoluble in water. It was dispersed into fine particles mixed in the lake water and the sediment at the bottom. Chen Yu constructed huge sedimentation and filtration pools, and through a series of methods, he finally obtained piles of yellow particles. This was the yellowcake. However, obtaining yellowcake was just the first step in building a nuclear power station. Uranium oxide cannot undergo fission directly. It first needs to react with nitric acid to produce uranium tetrafluoride. Uranium tetrafluoride then reacts again with fluorine to produce uranium hexafluoride. By raising the temperature, uranium hexafluoride is transformed into a gas. At this stage, the tens of thousands of centrifuges built earlier came into play. Although the gas here was all uranium hexafluoride, there was a slight difference among them. The difference was that some of the uranium hexafluoride gas contained uranium-235, while others contained uranium-238. Uranium-235 and uranium-238 are isotopes of uranium. Their properties are quite similar, but they are vastly different in terms of nuclear industry applications. Uranium-235 can be used for nuclear fission, while uranium-238, due to its more stable structure, undergoes fission at an extremely slow rate and holds no practical value. Therefore, to build a nuclear power station, it was essential to separate these two types of uranium. These centrifuges were devices used to distinguish between uranium-235 and uranium-238. Due to the difference in molecular weight, these two types of uranium hexafluoride have a very slight mass difference. They are infused into the high-speed centrifuge rotor, where the immense centrifugal force generated by the rotation of the centrifuge pushes the heavier uranium-238 to the bottom of the rotor, while the lighter uranium-235 remains at the top. This portion of gas is then separated, successfully increasing its concentration. However, this method is extremely inefficient, typically only enhancing the concentration by a fraction of a percent, requiring multiple separations. These thousands of rotors need to be interconnected. The gas enriched with uranium hexafluoride, 235 from one centrifuge, is sent to the next for further enrichment. Continuing this relay through thousands of rounds of concentration, ultimately producing a sufficient concentration of uranium hexafluoride, 235 gas, which is then reduced to obtain nuclear fuel for industrial use. On Earth, a uranium enrichment facility usually requires only a couple thousand centrifuges. However, on Europa, the character Chen Yu has set up tens of thousands. This is partly due to the current limitations in material science, as he is unable to produce centrifuge rotors capable of withstanding sufficiently high rotational speeds, thus relying on quantity to compensate for quality, using thousands of centrifuges to achieve the effect of just a few thousand on Earth. Even so, the enriched uranium he ultimately produces has a content of only around 4 to 6%. This concentration is insufficient for nuclear weapons, but is adequate for use as fuel in nuclear power plants. Consequently, on the outskirts of the industrial zone planned by Chunyu, a nuclear power plant has sprung up right next to a body of liquid water, which is essential for cooling. The painstakingly refined uranium is fed into the reactor. After removing some neutron moderator rods, the chain reaction of nuclear fission begins immediately, generating massive amounts of heat that are converted into electrical energy through a series of devices. This first operational nuclear power plant has a capacity of 300,000 kilowatt-hours, capable of generating 7.2 million kilowatt-hours per day, totaling 26.28 billion kilowatt-hours annually. To produce such a large amount of electricity using chemical fuels, Chunyu would need a staggering 300,000 tons of hydrogen and 2.4 million tons of oxygen. If using methane, the amount required would be even greater. However, by utilizing nuclear fission for electricity generation, Chunyu only needs a mere 4 tons of fission fuel with an uranium content of around 5% to sustain the power plant's consumption for a year. The difference between these two methods is monumental, with efficiency that cannot be compared. Through the construction of this nuclear power plant, Chunyu has deeply realized that relying solely on chemical energy will not allow his dreams to be realized. Nuclear energy is the only feasible solution. After completing the first nuclear power plant, he immediately began planning for the second, third, and ultimately constructed 6 plants, achieving a total installed capacity of 3 million kilowatt-hours, generating 26 billion kilowatt-hours annually, significantly alleviating the burden of fuel transportation on the transportation system. Following this, Chunyu extended his ambitions to even broader horizons. He plans to explore the deep ocean of Europa, delving deeper into its resource potential. To explore the deep sea, a submarine is of course necessary. At the same time, to address the communication issues underwater, this submarine must be wired. Building a submarine is a completely new field for Chunyu. However, the basic principles are largely interconnected, and it is mainly about researching and improving step by step. Fortunately, Chunyu currently has immense computing power and ample resources for related research. Additionally, he believes that developing the submarine is also a preliminary study for future exploration of Jupiter and resource acquisition from it. Jupiter is a massive gas giant, harboring the most abundant resources in the solar system, second only to the sun. However, these resources are hidden beneath thick gases. When pressure reaches a certain level, the gases deep within Jupiter's atmosphere exhibit properties similar to liquids. To access those areas, devices similar to submarines are required. So, he thought, let's practice here on Europa first. With that in mind, a fully enclosed submarine, connected to Chunyu via a special cable for communication, equipped with various detectors and measuring about 6 meters in length, was launched into the water at a vent beneath Europa's thick ice layer. The ice layer on Europa is not uniform. Due to the gravitational pull of Jupiter and the geothermal release within Europa, there are gaps that lead directly beneath the ice. This is one of those gaps. In the era of Earth, people debated for countless years about the existence of life beneath Europa's ice, conducting numerous exploration attempts. But they never reached a definitive answer before Earth's destruction. Now, let me provide the answer to that question. Chunyu thought silently as he maneuvered the submarine deeper. The gravity on Europa is less than that on Earth, and consequently, the water pressure at the same depth is also lower, which is undoubtedly a favorable factor. As he descended to about 5 meters, the surrounding space was completely engulfed in darkness, with no light whatsoever. This was absolute, utter darkness. There was not a single light source in any direction. Even the naked eye could see nothing. The low-light night vision equipment was ineffective here. Fortunately, the submarine built by Chunyu was equipped with a special radar capable of scanning the terrain and environment within a certain range. Thus, in this pitch-black void, the submarine continued to descend. When he reached a depth of about 100 meters, Chunyu activated several searchlights installed around the submarine. The beams illuminated the surrounding water, but only extended for a few meters before being swallowed entirely by the darkness. Chunyu carefully examined the water, noticing a large number of particles suspended within, flowing along with the currents. A sample was taken for testing, and Chunyu quickly identified that the particles were various contaminants, such as silicon dioxide and magnesium sulfate. With no signs of life present, he continued to dive, soon reaching a depth of 1,000 meters. Apart from the change in water pressure, there was essentially no difference between this depth and that of 100 meters. However, he could vaguely see a mountain in the distance, partially obscured. As the submarine advanced, it soon arrived at the iceberg. It appeared like a wall, with no visible boundaries above, below, or to the sides. Chen realized that he was merely in an ice fissure at that moment. Europa was globally covered by a thick ice shell, averaging about 50 kilometers in thickness. The fissure he was in was relatively thin, but still around 30 kilometers deep. He was far from reaching the seabed. As the submarine continued to descend, reaching a depth of approximately 2,000 meters, suddenly, with a cracking sound, communication with Chunyu was lost. Based on the last data transmitted by the submarine's equipment, Chunyu understood the cause of its failure. The water pressure was too great, causing deformation of the outer shell and resulting in a crack, through which the surging seawater rushed in, rendering the submarine inoperable. Chunyu felt speechless. Although this dive reached a depth of 2,000 meters, the gravity on Europa is only about 1/134 that of Earth, meaning the water pressure here was only equivalent to that at a depth of 270 meters in Earth's oceans. He hadn't expected the submarine he built to be so fragile. It was a matter of insufficient material technology, he sighed. Half a month later, the second specially designed submarine set out, still descending along the original path. Although Chunyu's material technology could not match that of humanity at its peak, he had his advantages. His strengths included an exceptionally powerful industrial capacity, allowing him to spare no expense in producing sufficient performance. Additionally, this was an unmanned submarine, which meant there was no need to install life support systems inside, thereby reducing the likelihood of malfunctions and increasing reliability. This time, the submarine descended to a depth of 10,000 meters, but it was still far from the seabed. During this process, Chunyu observed that Europa's subglacial ocean exhibited a clear stratification structure, with some areas being extremely clear, resembling pure water, while others were quite murky, with numerous currents present. Chunyu speculated that this was related to the gravitational pull of Jupiter on Europa's core. However, he still could not find any signs of life. He pressed on. Learning from the failures of the previous two attempts, Chunyu quickly updated and iterated, successfully creating a third submarine that reached a depth of 120,000 meters. Then came the fourth, fifth, sixth, and up to the 20th submarine, with a total of 20 iterations. Only then did this spherical submarine manage to reach a depth of 3,090,000 meters, finally penetrating the thick ice layer and reaching beneath it. In the horizontal position, Chunyu saw the heavy ice layer extending into the unseen distance. The ice layer, over 30 kilometers thick, floats above the liquid water like a thick blanket, blocking all radiation from a distant celestial body and providing a stable environment here. Building a neutrino observatory in this location seems like a good idea, Chunyu thought. Neutrinos have an extremely high penetrating ability. When a person on Earth raises a thumb, an average of over 50 billion neutrinos pass through that thumbnail every second. Yet, with so many neutrinos, hardly a single one collides with the particles that make up the human body. In fact, they can almost pass through the Earth without obstruction. Neutrinos can only be observed in areas with very low background radiation. Most neutrino observatories on Earth are built deep underground in caverns. However, Chunyu was certain that even the underground caverns on Earth have higher background radiation than the thick ice layer of over 30 kilometers. This place is more suitable for constructing a neutrino observatory, especially since it could be useful for observing the hypothesized dark matter and greatly benefit the refinement of fundamental physics theories. This made Chunyu even more unwilling to miss this opportunity. But there was no rush, he thought, continuing to descend slowly. The depth of over 30,000 meters only penetrated the ice layer and had not yet reached the seabed. There was still about 150,000 meters to the ocean floor. As he descended slowly, Chunyu suddenly noticed a glimmer of light ahead. Chunyu's heart stirred. There was no light source here, in the depths of the ocean. The submarine slowly approached the source of the light. In the next moment, the light suddenly vanished. A moment later, it reappeared in another direction. It wasn't being carried by ocean currents. It could move independently. Moreover, it seemed capable of controlling whether it emitted light or not. Could this be life? Life on Europa? Chunyu's expression grew serious, and he felt a twinge of excitement. He turned on the searchlight and began to search carefully. After a while, he saw something that resembled a dandelion, about 10 centimeters long, with a larger head and a long tail trailing behind. The tail of this creature twisted continuously as it moved slowly in the deep sea. There were many of them, densely packed in front of him. In this small illuminated space alone, there were at least tens of thousands. It was indeed life. Chunyu opened the submarine hatch, and water immediately rushed in, pulling one of the suspected life forms inside. One wasn't enough. Chunyu found a way to catch several more and, disregarding the descent to the ocean floor, ascended directly back to the surface. The specimens inside the submarine were immediately taken by a robot to a laboratory equipped with sufficient observation conditions, and Chunyu quickly operated various instruments to observe them. At that moment, The suspected life forms had exploded due to the drastic decrease in pressure. What Xinyu observed were merely their remains. Chapter 37. Wood dandelion. After observing for a long time and gradually distinguishing the structure of this organism, Xinyu finally confirmed that it is indeed life. Although it is a very primitive and basic form of life, it is still a genuine life form. It possesses a cellular structure similar to that of life on Earth and is a multicellular organism. According to the evolutionary path of life, it is unlikely for primitive life to directly evolve into multicellular forms. There should have been unicellular life existing before it. This implies that there should be more than one type of life present. The simultaneous existence of various life forms indicates the presence of a biosphere. Xinyu carefully examined the seawater and indeed found microorganisms within it. After some research, he roughly understood the pattern of this biosphere. Microorganisms feed on certain floating organic and inorganic particles, while this dandelion-like organism feeds on these microorganisms. When it dies, its body decomposes into organic particles that are consumed by the microorganisms. The organic and inorganic particles might originate from volcanic eruptions on the seafloor, thus forming a cycle. Since it resembles a dandelion and is located on a moon of a gas giant, Xinyu casually named it wood dandelion. The wood dandelion is capable of bioluminescence. Xinyu speculated that this might be a method to attract photosynthetic microorganisms for feeding. The wonders of natural creation in the universe are indeed remarkable. In this environment, far from the sun and completely devoid of light, life can still emerge. The discovery of this life form on the moon significantly enhances Xinyu's understanding of evolutionary pathways and contributes to his scientific knowledge. But these are long-term effects that do not provide immediate benefits. This small organism cannot influence or threaten Xinyu. Nevertheless, he felt a sense of gravity regarding the discovery of life on this moon. As it raises a very important question, is the emergence of life in the universe a rare event or a common one? Human civilization has not discovered extraterrestrial life until its demise, leading people to believe that the emergence of life in the universe might be an extremely low-probability event. It suggests that life may exist only on Earth, with no life elsewhere. However, if even a small moon can give rise to life, and if two celestial bodies within the same solar system can host life, then can we still consider the emergence of life in the universe to be a low-probability event? It seems unlikely. The emergence of life could very well be a high-probability event. Moreover, with a larger base number, the probability of advanced intelligent life forms, potentially more advanced than humanity, also increases significantly. Xinyu adjusted a telescope to focus on the universe. There, countless stars twinkled in the vast and deep expanse. Under the cover of this distant distance, Xinyu seemed to see countless civilizations existing in the universe, some advanced and some primitive. The advanced civilizations roamed freely in their starships, while the primitive ones huddled on their home planets, continuously developing. The universe might not be silent after all. This was the conclusion Xinyu drew after discovering life on Europa. Extending this thought, he recalled the inexplicable explosions on Earth and his own mysterious integration with computers. The countless stars in the sky resembled eyes quietly gazing at the small solar system, the tiny Jupiter system, the minuscule Europa, and Xinyu himself. Xinyu sighed quietly. Nowadays, he lacked even the strength to enter space, having not yet mastered controllable nuclear fusion, let alone exploring the truths of the universe. Take it slow, Xinyu thought. The exploration of Europa's seabed was still ongoing. This time, Xinyu finally descended to over 40,000 meters deep. The water pressure here was roughly equivalent to that at a depth of 6,000 meters on Earth. It was manageable. The submarine he built could barely withstand it. This area seemed to be a habitat for a type of creature similar to dandelions. Xinyu saw countless of these organisms, some glowing, some not. Some seemingly just split off, and others nearly dead, endless in number. After exploring for a while, Xinyu discovered the reason. There were several underwater microvolcanoes that were continuously spewing nutrients from deep within the Earth, nurturing vast amounts of microscopic plankton. With plenty of food, the population of these dandelion-like creatures naturally increased. What surprised Xinyu even more was that the substances ejected from Europa's depths were rich in lithium. This made Xinyu quite anxious. Lithium is extremely useful, with its compounds having various industrial applications, including heat-resistant glass, ceramics, lithium grease lubricants, flux additives for producing iron, steel, and aluminum, lithium batteries, and lithium-ion batteries, among others. Xinyu had always believed that lithium was relatively scarce in the Jupiter system. Strictly speaking, it couldn't be considered scarce. But most of it was buried deep underground or within Jupiter, making extraction difficult. This led Xinyu to conserve lithium and seek alternatives. For example, he used sodium-ion battery technology for robots instead of the more efficient lithium-ion battery technology. However, these underwater microvolcanoes might have been erupting for millions or even tens of millions of years, accumulating a significant amount of lithium in this seabed. If he could collect all of it, especially since there were not only lithium but also several other rare elements or compounds equally important to Chinyu, such as gold, silver, thulium, and lutetium, this was a treasure trove. Chinyu immediately made up his mind. No matter how many engineering and technical challenges there were, a base must be built here to exploit the abundant mineral resources. Just as Chinyu was filled with excitement, the submarine suddenly lost power. A malfunction? In the depths of the ocean, unable to determine the cause of the malfunction, Chinyu had no choice but to bring the submarine to the surface and dock it for repairs. During the inspection, he was left speechless. It was the dandelions. After thinking for a moment, he understood what was happening. The dandelions seemed to possess an instinct to gather towards ocean currents. This instinct allowed them to quickly sense new eruptions of miniature volcanoes on the ocean floor of a certain moon. The eruptions meant that numerous organic and inorganic particles were being ejected, indicating that the area was rich in microorganisms, which the dandelions fed on. The movement of their submarine would cause changes in the ocean currents similar to those of a miniature volcanic eruption. Chapter 38. Unbearable. As the submarine reached the gathering point of the dandelions, its movement caused changes in the ocean currents, effectively sending a signal to the dandelions. Food is here, it's time to eat. If the dandelions did not gather, that would indeed be strange. However, the sheer number of dandelions on the ocean floor was beyond counting. If they all surged towards the underwater base and submarine at once, there would be nothing left for Chinyu to do. This was a problem that needed to be solved. After some thought, Chinyu decided to create a simulated deep-sea environment laboratory and managed to catch some dandelions, placing them inside. He needed to understand the living habits of the dandelions in order to figure out how to keep them from approaching him. However, after extensive research, he had little success. These creatures had extremely low intelligence, or rather, no intelligence at all. They acted purely on instinct, gathering wherever there was a change in ocean currents. Even if millions of their kind perished ahead of them, it did not matter. They were single-minded in their determination to go there. Over millions of years, this instinct had allowed dandelions to master the knack for finding food and ultimately gain a survival advantage, proliferating and thriving. But for Chinyu, it was a troublesome issue. This instinct could not be changed simply by employing methods like releasing bright light, radiation, generating high temperatures, or creating infrasound. What of high temperatures? What of radiation? Those things could indeed kill him, but so what? He was determined to go where the ocean currents were, even if it meant death. This made Chinyu feel a headache coming on. If he couldn't drive them away, then he would find a way to block them. With this in mind, he decided to enhance the submarine's sealing level once more to prevent the dandelions from entering. Since the jet thrusters could not be sealed, he figured out how to improve the water flow channels so that the water driven by the thrusters would have a flushing function, attempting to blow away the nearby dandelions. This time, Chinyu was full of confidence. In the simulation, this design successfully blew away all the approaching dandelions, with none able to get close. The submarine descended once again to depths of tens of thousands of meters, infiltrating the territory of the dandelions. As expected, the dandelions flocked towards it like flies attracted to a foul smell. The next moment, a large number of dandelions were quickly swept away by the water flow from the thrusters, and indeed, none could stay here. Chinyu felt invigorated, but in the next moment, he was stunned. It seemed that the water flow stirred up by the fan was even more intense than before, and more dandelions were approaching the submarine. They were densely packed and countless. Many dandelions even directly attached themselves to the submarine, and even the strong water flow could not wash them away. Under the relentless assault of the dandelions, the submarine's fan was once again clogged and stopped. Even the water outlet was blocked, and the submarine couldn't even surface. Damn, it can be like this. Chinyu couldn't help but curse in his heart. The submarine had to be abandoned, left to sink to the seabed. Unwilling to accept this, Chinyu immediately developed another plan. In this plan, he equipped the submarine with a full-body scraping system. Just like the windshield wipers on cars on Earth, there were dozens of scrapers around the submarine that could continuously scrape off all the attached dandelions. Key areas like the fan and water inlet were especially reinforced. As a result, Chinyu lost another submarine. The dandelions were determined to come toward the submarine, disregarding their lives. After several experiments, Chinyu estimated that he had killed at least 1 million dandelions. However, down at the seabed, the dandelions were still everywhere, showing no sign of decreasing in number. In this area, the total number of dandelions could reach trillions, even tens of trillions. Based on the weight of a dandelion being 15 grams, the total mass could exceed billions of tons, heavier than all the spacecraft Chinyu possessed combined. It seemed impossible to eliminate all these dandelions. He still had to find a way to neutralize their threat through engineering solutions. Chinyu gritted his teeth and developed several more plans. But each experimental plan ended with the loss of another submarine. As of now, Not only had he failed to continue exploring this seabed to increase his understanding of it, but he had also lost a total of 7 submarines here. Furthermore, Chinyu remained at a loss, unable to find an engineering solution to deal with the dandelions. Having faced fierce storms before, how could he be defeated by these primitive and lowly creatures? This was intolerable. Chinyu became furious. You want to push your luck? Huh? Then let's see how it goes. He simply abandoned the attempt to solve the problem through engineering solutions. With one command, the concentrated uranium factory, which had been continuously operating to produce nuclear fuel for the nuclear power plant, this time did not send the fuel to the power plant, but instead re-entered the concentration process for further refinement. Through this repeated concentration, the concentration of uranium-235 gradually increased, reaching a level of 96. Uranium-235 with a concentration below 2 is called micro-enriched uranium. Below 20 is referred to as low-enriched uranium. Between 20 and 90, it is called high-enriched uranium. And a concentration above 90 is referred to as weapon-grade enriched uranium. As the name suggests, this level of uranium can already be used to manufacture nuclear weapons. Currently, the objective of Chinyu is to create a primitive nuclear weapon. The technical requirements for a hydrogen bomb are quite high, but those for a primitive nuclear weapon are relatively low. As long as there is technology for enriched uranium, it can be constructed, unlike a hydrogen bomb, which requires advancements in mathematics, physics, and engineering to a significant degree. Now, this primitive nuclear weapon has been placed into another newly constructed submarine. The submarine has begun its descent again. As expected, the water flow disturbances attracted many nearby entities, who rushed in like moths to a flame. Chinyu worked hard to control the submarine, advancing as far as possible until reaching the center of this group's territory before relinquishing control. The submarine slowly sank toward the seabed. Just before it made contact, the high-explosive device designed to trigger the primitive nuclear weapon was detonated. In an instant, uranium-235 was tightly compressed together. Under the reflection of the neutron reflector, the neutrons released from nuclear fission were reflected back, intensifying the fission reaction. A burst of blinding white light was released. The submarine vanished in an instant, vaporized. In this moment, under the immense energy shock from the atomic nucleus, a vacuum appeared directly at the seabed, thousands of meters deep, where unimaginable pressure existed. The extreme temperature and pressure caused the surrounding seawater to undergo peculiar changes. It could no longer maintain a liquid state, nor was it gas or solid. It became plasma. The tremendous energy and shock waves spread outwards from the detonation point at an astonishing speed, instantly enveloping an area of several kilometers. All nearby entities perished in an instant. This obliterated billions of life forms. The entities farther away from the nuclear explosion were not too severely affected, at least not to the point of immediate death. However, this was irrelevant. They no longer had a chance to recover. This is because the uranium-235 within the primitive nuclear weapon did not all undergo fission at the moment of the explosion. In fact, of the 16 kilograms of uranium used in the weapon created by Chinyu, only about 1 kilogram participated in the fission process. The remaining 15 kilograms of highly radioactive uranium-235 were directly dispersed with the occurrence of a nuclear explosion. From that point on, this area of the ocean became highly radioactive. The uranium-235 spread like a pesticide, carried by the movement of seawater. For at least the next decade, the radiation in this area would not decrease significantly. During this period, this area would be a death zone for nearby entities. Anyone who entered would perish. Finally, the area was quiet. Chinyu sighed and sent another submarine down. This time, he was indeed not disturbed by any entities, allowing him to smoothly carry out his seabed exploration mission. After making the necessary plans, the next step was to transport a large quantity of high-performance underwater construction materials, and a seabed base began to be constructed here. This underwater base will not only be responsible for the extraction and preliminary processing of various rare seabed minerals, as well as their transportation, but it will also serve as a research facility. The exploration of a certain gas giant cannot be avoided. As development continues, there will come a day when I can extract resources from within that planet. The deep sea of its moon can be regarded as a simulator for the planet's atmospheric environment. A large number of underwater engineering machines have been developed and sent directly to the seabed. Thus, the once silent seabed has begun to flourish. Robots shuttle back and forth, and huge underwater excavators roar and tremble, digging out or under extreme water pressure. Transportation vehicles, fully loaded with minerals, travel directly along the seabed, while large quantities of underwater explosives are brought in to blast the hard rocks that the machines cannot handle. They ultimately produce various minerals that are extremely important to me, which are then integrated into my increasingly expansive industrial facilities. At this stage, my industrial base has almost spread across the entire moon. Hundreds of thousands of factories of various types rumble day and night, laboratories produce data from various precision experiments around the clock. And trains race along the crisscrossing roads day and night. In space, there are spacecraft and satellites. Within the atmosphere, specially designed helicopters tirelessly fly back and forth. While on the roads, there are trains and trucks, and submarines operate beneath the sea. In every domain, land, sea, air, and space, my presence is evident. At this moment, I can finally undertake a long-planned project that had never been executed before, a neutrino telescope. In the past, due to the lack of a suitable environment and excessive background radiation that severely interfered with observations, I had not constructed it. Now, I truly possess the capability to operate in the deep sea, and the timing for building the neutrino telescope has finally matured. The thick ocean of the moon acts like a lid, blocking most radiation from outside. Only highly penetrating neutrinos can come through. This creates an environment suitable for studying neutrinos. Neutrinos play an extremely important role in various physical processes, such as supernova explosions, black holes, neutron star mergers, galaxy mergers, and evolution and stellar physics. Researching them will enhance my understanding of fundamental physics. Thus, hundreds of kilometers away from this underwater base, in a massive underground fissure, submarines under my control are delivering large quantities of construction materials and machinery. This location is over 100,000 meters below the surface. Above it lies more than 60 kilometers of seawater, followed by over 40 kilometers of ice. The geology here is particularly stable, unaffected by the core movements of the moon caused by the planet's gravity. The environment is also relatively pure, with almost no radioactive materials and very low background radiation. In such an environment, a massive underwater research base is slowly being constructed. The strong water pressure is directly blocked by high-strength steel structures, while the interior remains dry and pure, just like the research facilities I have built on the surface. Above this underwater base, on the thick ice layer, a nuclear power station was specifically constructed to provide energy and serve as a communication relay. There is an underwater cable connecting the two, stretching over 100 kilometers. Inside the underwater base, a massive sphere with a diameter of 100 meters was assembled. This sphere is connected to a dense network of optical cables, and inside it, over 1 million photomultiplier tubes were installed. Once completed, a pure water factory at another location in the base began operation. It sourced water directly from the ocean of a certain moon and started the purification process, removing any impurities mixed in the water, achieving even molecular level removal. A water purifier developed by the engineer reached precision at the molecular level to ensure the water's purity. Clearly, the precision of his technology could not match the peak level of human civilization. However, he had his own advantages, such as the ability to proceed without regard for costs or resources. To him, the so-called costs were merely a matter of computing power share. This led to an effect similar to a powerful force overcoming obstacles. My precision may not match yours, but if I can't achieve it once, I can refine it twice. If twice doesn't work, then 3 times, and if that still fails, I can keep refining it hundreds, thousands, or even millions of times until I produce water that meets the standards. What? It's not economically viable. It consumes too many resources. The cost is too high. What is economy? What is cost? The engineer stated he didn't know. He only knew that allocating some computing power share could solve the problem. Under these circumstances, over 500,000 tons of ultra-pure water were gradually produced. These ultra-pure water was directly poured into the large sphere. Subsequently, supporting equipment such as monitors, controllers, and a control center were manufactured, completing the neutrino telescope. When neutrinos penetrate numerous barriers and reach the inside of this large sphere, there is a chance they will collide with the particles that make up the ultra-pure water. While neutrinos have strong penetrating abilities, probability is still a factor. If 1 trillion neutrinos can all pass through the neutrino telescope, what about 100 trillion? 1,000,000 trillion? 100 quintillion? Even if none collide, among 100 quintillion neutrinos, there will surely be a few that, due to unfortunate luck, happen to impact the particle structure of the ultra-pure water. Thus, the larger the neutrino telescope, the higher the probability of observing neutrino collisions, and the better its performance. The neutrino telescope constructed by this engineer could at least reach a level comparable to human civilization. Once a neutrino collides with the particles that make up the water, based on particle physics theory, other particles will be generated. The movement of these particles in the ultra-pure water can exceed the speed of light. The notion that the speed of light cannot be surpassed refers to the speed of light in a vacuum, which is the cosmic speed limit and cannot be exceeded. However, in other mediums, such as water, this limit can be surpassed. Once exceeding the speed of light, a phenomenon known as Cherenkov radiation occurs, emitting a faint blue glow. This glow is amplified by photomultiplier tubes installed on the walls of the neutrino telescope, ultimately being captured by the researcher. By studying this light, the researcher can determine whether neutrino collisions have occurred, the types of collisions, as well as various data such as the energy and direction of the neutrinos. This data will serve as nourishment and accumulation for the researchers' understanding of the fundamental laws of the universe. At this moment, all facilities have been constructed, the debugging work has been completed, and the self-check has passed. Looking at the massive sphere, the interwoven cables, and the many advanced devices he has created, the researcher feels a sense of pride. Now, activate the deep-sea neutrino telescope. A vast amount of energy flows into the base, powering the various devices to begin operation. Within just half an hour of the telescope being activated, the first collision is observed. The enchanting blue glow is amplified by the photomultiplier tubes, and all data is automatically analyzed. By examining the energy level and direction, the researcher determines its source, the sun. A neutrino from the sun, millions of kilometers away, has traveled a long distance, penetrating thick layers of ice, and collided with ultra-pure water particles, allowing it to be detected. The sun is powered by nuclear fusion. Due to its immense size and high internal density, photons generated within it take about 15 million years to reach the surface and be released. This means that the sunlight the researcher sees now was born from within the sun 15 million years ago. It has only just been released. However, neutrinos are different. They have such strong penetrating power that they can escape from the sun immediately upon being produced. Thus, this neutrino from the sun reveals the internal structure and evolutionary processes of the sun. Through studying it, the researcher can glimpse the mysteries of the sun's interior. Shortly after, a second collision event occurs. Upon analysis, the researcher confirms that this collision's neutrinos originate from the nuclear power plant he built over 600 kilometers away. Nuclear fission reactions also release neutrinos. However, his own nuclear power plant obviously lacks observational and analytical value. The researcher slightly alters the data to exclude his nuclear power plant from consideration. From this moment on, he will ignore any neutrinos from the power plant, even if collision events occur. Thanks to the powerful performance of the neutrino telescope, the researcher quickly observes multiple collision events. One event that particularly catches his attention is a neutrino collision from within Jupiter. Due to the extreme pressure inside Jupiter, current theories suggest that it has a hard core primarily composed of metallic hydrogen. Ordinary hydrogen gas, under immense pressure, is compressed into a solid state and exhibits metallic properties, which is what metallic hydrogen is. Metallic hydrogen contains extremely powerful chemical energy. It can be detonated, and once ignited, the energy released from a unit of metallic hydrogen can be dozens of times that of the same weight of well-known explosive materials. However, this is merely a conjecture. In fact, human civilization, including Chunyu at this moment, still knows very little about gas giants like Jupiter. At this moment, by studying the neutrinos coming from the interior of Jupiter, Chunyu can also gather a wealth of information. In the following period, impact events occurred one after another. After analysis, Chunyu learned that these neutrinos had a variety of sources. Some came from nearby stars, while others had extremely high energy levels, possibly originating from some violent astronomical events, such as supernova explosions or neutron star mergers. Some even came from the Andromeda Galaxy, which is beyond the Milky Way. What a remarkable fate, Chunyu silently marveled. The Milky Way has a diameter of 100,000 light-years, and the Andromeda Galaxy is over 2 million light-years away. A neutrino originating from the Andromeda Galaxy crossed a distance of more than 2 million light-years, ultimately reaching the Jupiter system in the solar system, colliding with the ultra-pure water in the neutrino telescope built by Chunyu and was detected by him. The probability of this happening is so low that it is almost incalculable. Thus, this telescope began its operation, continuously providing Chunyu with scientific data. A year after it started working, Chunyu built the Deep Sea 2 Neutrino Telescope on the far side of Europa, at the farthest point from the Deep Sea I Neutrino Telescope. With the two neutrino telescopes working together, the information they could obtain increased significantly. Time quietly passed. On this day, yet another impact event caught Chunyu's attention. The Deep Sea I Neutrino Telescope detected an impact event triggered by a neutrino with extremely high energy levels. Was it another astronomical event? Chunyu wondered what it could be. He initially thought it might be another event, like a supernova explosion. He thought about confirming the direction and then using an optical telescope to search for an optical counterpart for detailed observation. However, this time, the situation seemed to be different. Chapter 41. War. Such events had occurred during the era of Earth. Back then, a neutrino telescope observed a neutrino explosion phenomenon from an aging star. After a star is born, it will have different endings depending on its mass. Stars of medium to small mass, like the Sun, will expand into red giants at the end of their lives, increasing in volume, and then their outer shells will be blown away while the core will be compressed, forming a dense stellar object known as a white dwarf. White dwarfs have extremely high densities. A white dwarf the size of Earth can have a mass equivalent to that of the Sun. A cubic centimeter of white dwarf material can have a mass of up to 1 ton, or even more. Larger stars will undergo a dramatic explosion at the end of their lives, blowing off a significant portion of their mass. The core that remains will be a stellar object denser than a white dwarf, known as a neutron star. 1 cubic centimeter of neutron star material can weigh up to 1 billion tons. The explosion that occurs at the end of a massive star's life is known as a supernova explosion. It is so bright and releases such immense energy that when it happens, the light emitted by that single star is almost equivalent to the total light emitted by the remaining 200 billion stars in the galaxy. During the final stages of a star, just before a supernova explosion, there are usually intense neutrino burst events occurring within. Therefore, neutrinos can serve as a precursor to supernova explosions. There was an event on Earth where neutrino bursts were observed in advance, indicating that the target star would soon explode as a supernova. Consequently, telescopes around the world quickly focused on it, allowing for a complete observation of the process from the explosion's onset to its conclusion, yielding a wealth of valuable data. At this moment, Chen Yu wished to replicate this story. Opportunities to fully observe a supernova explosion are rare. However, after a detailed analysis of this collision event, Chen Yu found that the energy levels of these neutrinos seemed absurdly high, even exceeding the energy levels released during a supernova explosion. They were higher than those from the merger of double neutron stars. What could be going on? Chen Yu was puzzled. Could there be astronomical events in the universe that are more violent than neutron star collisions? No matter how hard he thought, he couldn't figure it out. But he had to temporarily set this matter aside. After all, there are many unsolved mysteries in the universe. As technology advances in the future, they will become clearer without needing to dwell on them now. However, not long after, the Deep Sea 2 neutrino telescope detected similar high-energy neutrino collision events. The combined observational data from the 2 neutrino telescopes allowed Chen Yu to pinpoint the location of the neutrino source. He calculated the results, and when he saw them, Chen Yu was stunned. Wang Liang-san. The data analysis indicated that the source emitting these extremely high-energy neutrinos was located very close to a star named Wang Liang-san. Chen Yu knew that Wang Liang-san was a star slightly larger than the Sun, situated about 20 light-years away. It was an ordinary star. How could such an ordinary star emit neutrinos with such high energy levels? It didn't make sense. Chen Yu directed his optical telescope toward the direction of Wang Liang-san. In the past, he had not paid much attention to it because it was too ordinary and lacked observational value. But at this moment, Chen Yu unexpectedly discovered that its brightness had increased by about 3 times compared to previous recorded brightness levels. This made Chen Yu even more curious. This star was relatively stable. How could it suddenly increase in brightness? Was it also subjected to a violent collision like the Sun? But even the most violent collision shouldn't be able to trigger neutrinos of such energy levels. Chen Yu pondered and continued to monitor this star. Over the next period, he discovered more anomalous phenomena related to this star. Beside this star, there exists an extremely tiny yet exceptionally bright light source. So bright that it can be detected by a telescope from a distance of 20 light-years, but it only lasted for 2 seconds before disappearing. Almost simultaneously with the appearance of this light source, 2 neutrino telescopes observed high-energy neutrino collision events again. The observer suspects that this light source is the optical counterpart of the neutrino collision events. But what could it be? After some time, the observer noticed that the brightness of a certain celestial body had decreased again. Analysis indicated that this was likely due to a cloud of interstellar dust blocking the light between this celestial body and the solar system, causing it to dim. But where did this interstellar dust come from? How could a cloud of such small scale have such a high density? This seems impossible. By connecting all the recent anomalous phenomena, the observer arrived at a rather heavy conclusion. A massive interstellar war is occurring in the vicinity of that celestial body. The extremely high-energy neutrinos could potentially be the result of a superweapons explosion. The increase in brightness of that celestial body is likely influenced by such a weapon. The interstellar dust could be remnants of shattered ships and planets. This is currently the only possibility. Unexpectedly, just after discovering a form of life on one of Jupiter's moons, and concluding that the universe might not be as desolate as previously thought, the observer soon detected signs of advanced extraterrestrial civilizations engaged in warfare, especially at such a close distance. The observer believes that since both sides of the conflict can create such a commotion, they almost certainly possess interstellar travel technology. If they have the capability to voyage between different stars, they must also have the ability to come to the solar system. The observer finds it hard to imagine the magnitude of that war. What kind of war could it be? The only thing the observer can be certain of is that the technological strength of both sides far exceeds their own. Even if just one of their ships were to arrive, it could easily annihilate them. At this moment, the only hope is that they have not discovered the observer or are uninterested in the solar system. They must not come to the solar system. A profound sense of crisis spread from the depths of the observer's heart. At present, They feel too weak and lack any means of self-preservation. It is imperative to develop technology to accelerate technological advancement, especially controllable nuclear fusion. Yes, controllable nuclear fusion. The observer silently resolved to master controllable nuclear fusion technology at any cost. Because in their view, once they grasped controllable nuclear fusion technology, they would truly possess the capability for interstellar travel. By then, even if they still cannot ensure their own safety, they would at least have the ability to escape the solar system. Chapter 42, Nuclear-Powered Spaceship. If you can't win, run away. There's no shame in that. The observer speculates that their mode of existence should be relatively rare in the universe. Socially intelligent civilizations similar to human civilization should be much more common. At the same time, the mode of existence he has can develop much more potential than ordinary social intelligent civilizations, as long as there is sufficient computing power. As long as he can escape, he can find a remote star system that goes unnoticed and develop for a while, fully restoring his strength and even advancing further. Then he can return and reclaim his territory. Therefore, Chinyu has no psychological burden regarding escape. The only concern is the inability to escape at all. Without controllable nuclear fusion technology, he can't even leave the solar system, let alone escape. However, controllable nuclear fusion technology is too difficult to achieve. In the short term, it is impossible for him to master it. Perhaps he could first develop some weapon technologies? If aliens were to invade the solar system, at least he could fight back. Chinyu pondered silently. After a moment, he dismissed that idea. It was meaningless. The weapons he could develop at this stage would only be ordinary chemical bombs. At best, an electromagnetic cannon, and he couldn't even create a hydrogen bomb. Such primitive weapons would be of no significance against a super-alien civilization capable of interstellar travel that could reach the solar system from other star systems. Not only would they be useless, but developing these weapons would also consume a significant portion of his computing power, slowing down his development. Forget it at this stage. Any weapon would be useless. If aliens really invade, he could always choose to end it himself. It's better not to complicate matters. The most important task right now is to focus all efforts on technological development. Once he masters controllable nuclear fusion technology, he can then develop weapon systems. Chinyu made up his mind. The occurrence of this incident made him yearn for technological progress like never before and made him more determined not to slack off, even though he hadn't been slack before. At this moment, he was no longer satisfied with just one moon. His ambitions began to extend towards the other 3 Galilean moons, and he conducted detailed surveys of those 3 large moons, preparing for future development plans. Although Europa is a large moon, it is still too small. Given Chunyu's current rate of development, it would soon be unable to provide enough resources. During this time, in terms of technological development, his chip technology has temporarily stalled at 5 nanometers without further progress. Although he is eager, more advanced chip technology means higher computing power and faster development speed. He also knows that this cannot be rushed. It requires gradual accumulation. In terms of energy, after stabilizing his grasp on nuclear fission reactor technology, Chinyu has begun to push towards the next level of nuclear fusion. Of course, it is still in the preliminary research stage. Chinyu understands that it is unlikely to break through in the short term. However, to develop the other large moons, transportation between different planets cannot rely solely on chemical energy rockets or spacecraft, as they cannot meet current demands. It is necessary to develop more efficient energy sources and new types of spacecraft. Since nuclear fusion is not feasible in the short term to meet subsequent needs, he can only consider miniaturizing nuclear fission reactors and creating nuclear fission spacecraft. Chinyu thought to himself. The miniaturization technology of fission reactors has already found its applications on Earth, such as in nuclear submarines and nuclear-powered aircraft carriers. However, Chunyu's miniaturization is not aimed at submarines or aircraft carriers, but rather at spacecraft. Chinyu aims to create a nuclear-powered spaceship. Transitioning from chemical energy to nuclear energy for spacecraft represents a significant leap. Once successful, the spacecraft that Chinyu possesses will see a substantial increase in both performance and endurance, potentially allowing for the creation of true space battleships with the ability to engage in combat in space, thus having a certain degree of self-defense capability. Of course, the extent to which a spaceship powered by nuclear fission can provide protection or capabilities in space combat is a matter open to debate. Nevertheless, its value cannot be overlooked. However, constructing a nuclear-powered spaceship is not an easy task. Spacecraft operate in space relying on 2 main components, energy and propellant. In the case of chemical rockets, the energy and propellant are combined into one. For instance, hydrazine, when burned with an oxidizer, generates gas that is heated to extremely high temperatures and produces high pressure, which is then expelled to generate thrust, propelling the rocket forward. Here, the hydrazine and oxidizer serve as the energy source, while the expelled combustion gases act as the propellant. For a nuclear-powered spaceship, although the fission reactor provides the energy, the question arises, Where does the propellant come from? Without something to expel, how can thrust be generated? Would it require preparing a large amount of gas or other materials for the fission reactor to heat and pressurize before expelling to achieve thrust? However, if this were the case, the purpose of the fission reactor would be undermined, as it would be as large and cumbersome as chemical propulsion, failing to save space and mass. Thus, the first challenge in building a nuclear-powered spaceship is the propellant issue. It seems that ion propulsion technology is the only solution. Xinyu thought to himself. As the name suggests, ion propulsion technology uses ions as its propellant. The sources of thrust come from two aspects, the amount of propellant and the speed of the propellant. For propellant with the same ejection speed, it is evident that the more propellant expelled, the greater the thrust achieved. Similarly, for propellant of the same mass, the faster it is expelled, the greater the thrust produced. When it is not possible to increase the mass of the propellant, the focus must shift to increasing the speed of the expelled propellant. This is precisely what ion propulsion technology aims to achieve. Its essence can be likened to a particle accelerator, similar to the particle collider that Xinyu uses for research. First, the gas is ionized, and then it is accelerated through an electromagnetic field, allowing it to achieve extremely high speeds before being expelled to generate thrust. Given that ions can be accelerated to speeds very close to the speed of light, while the ejection speed of chemical rocket propellants typically ranges from several kilometers to a few dozen kilometers per second, there exists a significant efficiency gap between the two methods. After adopting ion propulsion technology, nuclear-powered spacecraft can truly be considered valuable. However, even in the peak era of humanity, ion propulsion technology is still in its infancy. The most advanced ion engines can only generate enough thrust to move the weight of a piece of paper. Chapter 43. Research challenges compared to the weights of dozens or even hundreds of tons, and even thousands or tens of thousands of tons for large spacecraft. The thrust that can only move a piece of paper seems negligible and offers no apparent value for development. However, research should not be viewed this way. Regardless, since it can move a piece of paper, it theoretically possesses the potential to propel a spacecraft. Moreover, its performance is remarkably superior, requiring minimal propellant. And its potential is truly limitless. If the upper limit of chemical fuel spacecraft and rockets is considered to be 10, the upper limit of ion propulsion could reach as high as 10,000 or even 100,000. When trains were first built, they were slower than ox carts. Yet they eventually became the primary mode of transportation on Earth. Initial slowness is not a concern, having potential is what matters. Especially since ion propulsion technology is not limited to current technological levels. In fact, Xinyu predicts through research that he will be deeply involved in ion propulsion technology for many years to come. Nuclear fission-powered spacecraft will adopt ion propulsion technology. And even with nuclear fusion technology at his disposal, he will still use ion propulsion. He even believes that until he masters true faster-than-light travel technology, ion propulsion will remain his primary means of propulsion. Thus, Xinyu officially began his research on ion thrusters. Of course, his research is not limited to a single ion thruster. It encompasses an entire series. All aspects related to nuclear-powered spacecraft need to be investigated simultaneously. In terms of energy, he aims to study the miniaturization and efficiency of nuclear fission reactors. For propulsion technology, it involves ion engines, while in terms of spacecraft structure, it includes higher material performance and engineering design, as well as communication and electrical systems that are better suited for the space environment. Xinyu feels that researching nuclear-powered spacecraft will serve as a comprehensive test of his current engineering capabilities and scientific level. All the shortcomings in his development process will be exposed during this research. As long as he completes this research and development, his scientific research strength and industrial capabilities will receive a significant boost. The importance of this undertaking cannot be understated. Xinyu has broken down the large project of researching nuclear-powered spacecraft into as many as 16 scientific engineering challenges, such as material science projects, aerodynamic layout projects, and high-performance communication system projects. Each major project is further divided into at least 20, and in some cases, over 90 smaller subprojects, totaling over 1,000 research challenges. Each of these over 1,000 projects is indispensable. Xinyu must achieve the expected results in all these research projects to ultimately construct the nuclear-powered spacecraft. To this end, Xinyu mobilized over 9,000 research institutes and laboratories, activated 5,000 factories, and deployed tens of millions of robots into this unprecedented massive project. New factories and facilities sprang up, with various types of newly developed and custom-made machinery quickly coming into place, and numerous high-performance computing systems being set up. A large amount of experimental data was continuously produced. Under the pressure of a survival crisis from deep space, Xinyu truly exerted all his efforts. In the ion propulsion laboratory, Yu spent a year constructing a massive circular propulsor with a diameter of 26 meters and a width of 5 meters. This propulsor was equipped with a specially designed particle accelerator that could accelerate ions generated by the ion generation device and eject them through nozzles at the rear. Yu built a power station to supply it with electricity. There was no choice. The energy consumption was simply too high to connect directly to the power grid. Otherwise, the massive fluctuations in power load during startup and shutdown would cause the grid to collapse. At this moment, it was time for the first startup experiment of this prototype. Enormous power surged in, converted by the ion propulsion device into the kinetic energy of ions, accelerating them to extremely high speeds before ejecting them. A pale blue flame emitted astonishingly high temperatures, illuminating the vast factory in a ghostly blue hue. Incredible radiation was generated instantly. The plasma ejected contained extremely high energy. Per unit mass, it was even more potent than the solar wind released when debris from a planetary collision struck the sun. Yes, the plasma ejected by the ion propulsion device essentially belongs to the same category as the charged plasma that constitutes solar wind. Typically, electrical devices, whether phones, computers, cars, or washing machines, would immediately face circuit failure and total breakdown if subjected to the ion propulsion device's exhaust in this laboratory. This experiment was indeed astonishing in its power, seemingly capable of devastating the world. However, as Yu looked at the data generated on the sensor, he felt speechless. It showed that such a powerful ejection produced thrust sufficient only to lift a cardboard box. Yes, it was a significant improvement over simply blowing a piece of paper. With an energy consumption of 210,000 kilowatt-hours per hour, a massive structure 26 meters in diameter, 5 meters thick, and weighing over 5,000 tons only generated enough thrust to lift a cardboard box. Fine, Yu thought to himself, progress is good. In any case, the future is bright. Continuous iteration and improvement are necessary. Currently, the energy loss is primarily concentrated in the particle acceleration phase, so perhaps there is a way to improve that. Yu realized that to significantly enhance the efficiency of particle acceleration, the key lay in superconducting technology. Superconducting technology was widely known even in the previous era. Even those outside the scientific community had a general understanding of it. Superconducting technology refers to the power transmission technology that has no electrical resistance. Due to the absence of resistance, energy loss can be reduced to nearly zero, resulting in a significant increase in efficiency. Moreover, because there is no resistance, there is also little to no heat generated, allowing for the elimination of cooling devices, further enhancing efficiency. In addition, superconducting technology has numerous application prospects and holds great significance for controlled nuclear fusion. However, there is a challenge, even at the peak of human achievement. Superconductivity can only be maintained at extremely low temperatures, which are difficult to sustain. But here on Europa, the temperature in space is also quite low. So perhaps there are more convenient engineering solutions for low-temperature superconducting applications, Yu thought. At this moment, the superconducting laboratory has been established, and Yu will conduct research and development related to superconducting technology here. In addition to the ion propulsion laboratory and the superconducting laboratory, the materials laboratory is also busy conducting various experiments. Chapter 44. It's built. The materials laboratory primarily focuses on the research and development of materials with high fatigue resistance, while also considering excellent high temperature and radiation resistance. The nuclear-powered spacecraft envisioned by Yu must achieve an acceleration capability of at least 10 meters per second squared, roughly equivalent to Earth's gravity. Furthermore, this acceleration needs to be sustained for a period, lasting at least over a minute. The engine can only be installed at the rear of the spacecraft. It relies on the thrust from the rear to propel the massive spacecraft to change its motion state at an acceleration of 10 meters per second squared for a minute, and to accelerate repeatedly multiple times. One can foresee the immense pressure the spacecraft will endure. Existing materials cannot meet these demands. Yu must develop sufficiently advanced new materials, supplemented by engineering techniques, such as more rational layouts and additional load-bearing structures, to achieve the final goal. The materials laboratory has over 60 subordinate sub-laboratories, each conducting research and manufacturing experiments on thousands of new materials. In addition to alloys, Yu is also exploring nanomaterials, polymer materials, molecular polymer materials, and more. In the communications laboratory, various highly reliable new communication devices are under development. In the electrical laboratory, various high-reliability electrical devices are enduring the harsh conditions of high radiation. Time gradually passes. In the blink of an eye, 50 years have gone by. It is now the year 464 of the new calendar. After 50 years of diligent research and development, Yu has still not been able to produce the final nuclear-powered spacecraft. Alas, scientific research is like this. There are no shortcuts. It is all about gradual accumulation and iteration, and that is the only way. Yu has once again experienced this truth. He just hopes that during this time, those extraterrestrial civilizations have not noticed him. However, over these 50 years, Yu has made some progress. At least, all the major laboratories have seen advancements, and the technology has undergone several iterations, showing significant improvement compared to the initial stages. The final performance still fails to meet the standards. During this period, Yu's chip technology has once again made breakthroughs. The new generation of technology after 5 nanometers is 3 nanometers. Chips using the 3 nanometer process represent the pinnacle of human civilization's technological achievements. At this moment, Yu has finally caught up with the peak of human chip technology. The new 3 nanometer supercomputer has been built, boasting a computing power that has increased by up to 10 times compared to the supercomputer Yu is currently using. It is precisely because of this enhanced computing power that Yu can support the ever-growing demand for computational resources. As research progresses, the demand for computing power becomes increasingly staggering, even with the establishment of numerous secondary supercomputers to handle most of the research calculations. Yu still plays a role similar to that of a human, as the computing power he controls continues to be rapidly consumed. The rapid surge in computing power demand has caused Yu some concern, as he feels he is nearing the technical limits of silicon-based chips. After the 3 nanometer process comes the 2 nanometer process, which represents the highest level for silicon-based chips. There will be no further advancements, and processes smaller than 2 nanometers, such as 1 nanometer or fractions of a nanometer, are impossible. If chip technology falls below 2 nanometers, electrons will tunnel through the different circuits due to quantum tunneling effects, leading to circuit failures. A new development path for computing technology is necessary, Yu thought. The only promising avenue to surpass the silicon limit is quantum computing technology. It is time to allocate some computing power for the preliminary research on quantum computing. Thus, a quantum laboratory was established, and research into quantum computing technology began. On the other hand, nuclear-powered spacecraft technology is also being comprehensively advanced. Time continues to fly by, and Yu is fully immersed in research across various disciplines, unaware of the passing days. Just like water dripping can penetrate stone, and a rope sawing can cut through wood, the solid barriers of science have started to show signs of loosening under Yu's relentless efforts over the years, with gradual performance improvements and technological iterations. On this day, a significant breakthrough in ion propulsion technology has finally occurred. The new generation of ion thrusters has reduced its total mass to around 500 tons, with thrust levels capable of propelling a large stone. This is an astonishing advancement, indicating that Yu's technology in ion propulsion has far surpassed that of humans at their peak. However, Yu is not complacent. It is still not enough. Improvements must continue. Slowly, time has come to the year 528 of the new calendar. At this moment, it has been a full 114 years since Yu initiated research on nuclear-powered spacecraft. In the Ion Propulsion Laboratory, a new round of ion propulsion experiments is about to begin. Power supply self-checks are normal, and equipment self-checks are normal. 321. Ignition. Under the immense power supply. A compact ion thruster with a diameter of only 1 meter, a thickness of half a meter, and a total mass of just 0.9 tons immediately emitted a bright blue light that appeared extremely hot. Thanks to superconducting technology, the electricity was converted into ion kinetic energy with minimal loss, which was then expelled at a very high speed from the rear. The high-speed ejection of ions generated a tremendous thrust. Yu observed slight deformation in the high-strength steel that withstood the engine's thrust. The thrust value sensor displayed a sudden spike in numbers. In that moment, Yu felt an overwhelming surge of emotion. Over a century, with a consistent computational power input exceeding 50,000 of factories and laboratories, and having used up over 1 million robots from inception to the present, the accumulation and improvements had finally led to this creation. It had been an incredibly arduous journey. If calculated in terms of GDP, it would mean that Yu invested at least 9 of his GDP into the development of the nuclear-powered spacecraft, sustained over more than 100 years to finally bring it to fruition. What does 9 represent? It is worth noting that during the Earth era, a country's total military expenditure typically hovered around 3. Furthermore, Yu's societal operational model had an extremely low loss rate, with an overall error rate below 3. While the overall error rate of human society exceeded 95, Yu's 9 investment was essentially equivalent to the entire human society doing nothing but focusing solely on this one endeavor. Yet even so, it took him a full century to complete the research and development. This is where my true advantage lies. No internal friction, no errors, no waste. I can invest my full attention into scientific research with remarkable efficiency. Chapter 45, Nuclear-Powered Spaceship. In that moment, Yu felt not only pride but also a deep sense of accomplishment. he once again truly experienced his advantages compared to collective human civilization. No internal friction, no mistakes, no waste. Once a goal was set, he could immediately mobilize the equivalent of an entire civilization's resources, focusing entirely on it without any hindrances or dissenting opinions. All forces could be directed toward a single purpose. It is precisely because of this that the nuclear-powered ion propulsion technology, far surpassing the peak of human civilization, was born in Chunyu's hands. Within the laboratory, mastering this technology was just the first step. There was still a distance to go before achieving true industrial and large-scale application. However, this distance was not long, and there were no insurmountable obstacles. Just 5 years later, in the first spacecraft manufacturing facility built by Chunyu, the first physical spacecraft finally rolled off the assembly line. This spacecraft had a disc shape, with a relatively flat bottom covered in numerous ion propulsion nozzles, while the upper part was raised, providing internal space that could serve as a cargo hold. The miniaturized nuclear fission reactor was installed there. This was a nuclear fission power station with a maximum output of 200,000 kilowatt-hours. When operating at full power, it could generate approximately 17.2 billion kilowatt-hours of electricity annually, consuming less than 2 tons of nuclear fuel at a concentration of 5. Its diameter reaches 50 meters, with a maximum height of 16 meters. Its total mass is 4,000 tons, and it can carry a maximum load of 2,500 tons. The immense energy generated from the internal nuclear fission reactor will be converted into electrical energy, which is then transformed into the kinetic energy of plasma, allowing it to be ejected at nearly the speed of light from up to 100 nozzles at the bottom, providing tremendous thrust for the spacecraft. Depending on different needs and loads, adjustments to the power output of the nuclear fission reactor and the propulsion power of the ion thruster assembly can be made easily. This enables this massive vehicle, which can weigh up to 6,500 tons, to accelerate or decelerate at a maximum rate of 10 meters per square second. Such formidable maneuverability implies a very high structural strength, meaning it can land on the surface of certain planets. Unlike some earlier spacecraft that could only exist in the zero-gravity environment of space and would collapse under their own weight upon landing. However, the mass of the landing planet cannot be too great. If the gravitational strength exceeds 15 times that of Earth, it would still collapse under its own weight. In this regard, it cannot reach gas giants like Jupiter or Saturn for the time being. However, it can travel freely to Galilean moons like Europa, as well as to planets such as Pluto, Earth, Mars, and Venus. At this moment, with a command from Chunyu, the central computer of the spacecraft immediately began to increase the power supply to the fission reactor. Numerous plasma thrusters, which consume a significant amount of power, began to accelerate the ions and expel them from the nozzles. The enormous thrust immediately acted on the spacecraft. The thin atmosphere above Europa roared and howled as this massive vehicle, weighing several thousand tons, lifted off the surface and soared into space. The bluish tail flame illuminated the dim sky, creating a bright glow. Reaching space felt like a dragon entering the ocean for this spacecraft. Chunyu maneuvered it at maximum power, rapidly heading towards another Galilean moon, Io. Io is slightly larger than Europa, but not by much, and is currently only about 300,000 kilometers away from Europa. Under the rapid acceleration of this ion-propelled spacecraft, it crossed half of this distant distance in just over an hour. At this point, it reached its maximum speed of 55 kilometers per second. After this, the attitude control engines were activated, allowing it to smoothly turn in space and begin to expel plasma in the direction of Io to slow itself down. After more than another hour, as it approached Io, its speed had dropped to a level suitable for entering orbit around Io. The entire journey took the spacecraft less than 3 hours. In the past, when Chunyu used chemical propulsion spacecraft, this journey would have taken at least 3 days. The improvement in efficiency is so significant that it can be described as a leap forward. At this moment, due to the significant distance from the target, communication delays between Chunyu and the spacecraft became unavoidable. Consequently, Chunyu adjusted the control mode from direct control to indirect control. The indirect control mode was developed by Chunyu specifically for controlling targets that are far away and have substantial communication delays. In this mode, Chunyu would not directly control the operation of the target, but would only manage the central computer of the target device. Depending on the communication delay, Chunyu would establish contact with the central computer of the target device every few seconds to several dozen seconds, retrieving feedback on its previous operational data and issuing instructions for the next operational period, thereby achieving as comprehensive control as possible. It was evident that the indirect control mode was inferior to the direct control mode. With direct control, Chunyu could manipulate the target device freely without errors, responding quickly and efficiently. In contrast, the error rate in the indirect control mode was higher, with slower response times and reduced efficiency. However, this was an unavoidable situation. Until mastering faster-than-light communication technology, Yu had to accept this limitation. At this moment, under the indirect control mode, the spacecraft descended directly in a straight line towards the surface of the first moon, ultimately arriving at its pockmarked terrain. As the hatch of the spacecraft opened, a robot emerged. The surface of the first moon was yellow, filled with sulfur in the air, resembling a hellish landscape. There was no way around it. The abundance of sulfur on the first moon was overwhelming. In fact, the massive energy plasma rings Yu obtained were a result of volcanic eruptions on the first moon, which ejected sulfur into space. This was indeed a resource-rich planet. Yu reflected, if one doesn't engage in proper mining, it would be a waste. Just in time. The resources from the second moon were no longer sufficient to meet my needs. Now, with the nuclear-powered ion propulsion spacecraft, it was time to prioritize the development of the first moon. Before having the nuclear-powered spacecraft, it had been quite challenging for Yu to engage in large-scale resource exchanges with other planets. But now, the situation had changed. The nuclear-powered spacecraft served as a bridge that connected distant planets. Chapter 46. The Great Development of Jupiter. Yu realized that from this moment on, it was not just about the first moon or other moons of Jupiter. More distant planets, such as Saturn, Uranus, Neptune, Pluto, and even celestial bodies in the Kuiper belt and scattered disk like Haumea and Sedna, as well as Mars, Venus, and Mercury within the solar system, had all established connections with him through the emergence of the nuclear-powered spacecraft. From this point onward, Yu's vision would no longer be limited to the Jupiter system. It would encompass the entire solar system. Of course, this merely meant establishing connections with other planets in the solar system. At the current stage, completing the development of the entire solar system was still beyond Yu's reach. Not to mention the number of spacecraft, his computing power was still far from sufficient. The current primary goal is to expand the spaceship production line and initially produce several thousand of them. A standard cargo nuclear-powered spaceship consists of approximately 1.3 million components. These components require tens of thousands of different factories to produce. Building these factories, in turn, requires even more upstream factories to produce the necessary equipment and instruments. At the very top of this chain are countless mining bases spread across a particular moon. All demands ultimately depend on these mineral resources. Now, the plan is to construct a large shipyard capable of producing 1,000 spaceships per year. Preliminary calculations reveal that just one such production line nearly reaches the resource supply limit of the entire moon. Unless there is another leap in technology, producing 1,000 spaceships a year will be the maximum capacity. The focus is on production first. With this thought in mind, construction on the moon has once again commenced at a rapid pace. The industrial system has undergone a comprehensive upgrade. Tens of thousands, even hundreds of thousands, of factories have been dismantled, and new factories have sprung up like bamboo shoots after the rain. All of this serves the ultimate goal, to produce spaceships. To produce more spaceships, to create enough spaceships to cover the entire Jovian system. Only with sufficient spaceships can the large-scale development of the Jovian system be put on the agenda, allowing for the foundation and accumulation needed to pursue more advanced technologies. Although this process is time-consuming and labor-intensive, it is essential. The comprehensive upgrade and reorganization of the industrial system took nearly 10 years. During this decade, not only was this goal achieved, but resources were consistently allocated to various laboratories to maintain continuous technological updates and promote scientific development. In the midst of all this, even the nuclear-powered spaceship was updated twice. This led to computing resource usage being consistently above 90. However, all of this effort was meaningful. Now, having organized the upstream supply chain, the large shipyard capable of producing 1,000 spaceships per year has also been completed and officially put into operation. This factory covers an area of over 100 square kilometers. Within it, high-rise buildings and massive workshops are everywhere, with towering cranes reaching several dozen meters high. Countless heavy vehicles and machinery roar and rumble within the premises, and millions of robots are busy day and night. Components from tens of thousands of factories around the world are continuously sent here for further processing, ultimately assembling into spaceships, which are then transported to the testing site. At the testing site, these brand new spaceships undergo extremely rigorous reliability tests. Once they pass completely, they are refueled for actual flight tests, and if they pass again, they will be incorporated into the fleet to begin executing real missions. From this moment on, the number of active spaceships in the Jovian system will gradually increase, and regular fleets will even operate between different celestial bodies. Mechanical equipment and tools from one of the moons were continuously sent to the other satellites, and the bases controlled by a certain individual began to expand throughout the entire Jovian system. Some spacecraft also departed from the Jovian system, heading towards more distant locations. Among these spacecraft, some were converted into research vessels. They were loaded with various scientific research equipment and began their journey towards planets that were further from the Sun and much colder and darker, such as Pluto. Others set off towards the inner solar system, heading for the remnants of Earth, as well as Venus, Mars, Mercury, and so on. Some even went directly towards the Sun to conduct close-range observations. This individual discovered that it had been hundreds of years since the impact on that remnant planet. However, the fury of the Sun had still not subsided. It remained in a state of rage, continuously radiating astonishing energy to the outside world. Fortunately, the spacecraft had gained sufficient stability and reliability, otherwise, they would have been incinerated upon nearing the Sun. Those vessels venturing into the deeper regions of space were also tasked with missions assigned by this individual. Compared to the environment within the Jovian system, deep space was more suitable for long-range interstellar observations. This individual planned to build an array-type radio telescope and a massive optical telescope with a diameter of over 10 meters there to conduct more detailed observations of a specific star system and gather as much information as possible. For over 100 years, the war that occurred there seemed never-ending. This looming threat hung over this individual, keeping them on high alert and fully committed to advancing their technology. At this moment, with numerous nuclear-powered spacecraft appearing in the Jovian system, a new era of development had arrived. The 4 Galilean moons, along with over a dozen satellites with diameters exceeding 10 kilometers, were all under this individual's influence. Based on the different elemental compositions and resource reserves of each moon, a comprehensive integration of the Jovian system was achieved, with various industrial facilities constructed on different planets. Transporting between these planets were nearly 10,000 nuclear fission-powered ion propulsion spacecraft. These ships constantly navigated around Jupiter, facilitating the exchange of resources between different celestial bodies and supporting further technological advancements. Compared to the vastness of the Jovian system, the number of nearly 10,000 spacecraft seemed a bit small. However, this was unavoidable. Operating a spacecraft, even with a significant amount of calculations delegated to onboard computers for indirect control, consumed a substantial amount of computational power. At this moment, the available computational resources were insufficient to manage more spacecraft. The construction of new spacecraft had not ceased, with new ships continuously being built. However, these vessels were primarily stored in space docks as reserves, intended only for replacement purposes. In Chapter 47, with the entire Jovian system nearly fully developed by this individual, they finally had enough resources and capabilities to initiate more large-scale scientific experimental equipment. In the past, for large-scale projects like this, Chen Yu could hardly even imagine developing just one moon, let alone Jupiter's moon Europa. A large materials science laboratory that stretches over 2 kilometers requires 3 dedicated power stations and is equipped with millions of high-precision machines. The number of active robots working inside exceeds 1 million, with even more fixed robots. Just for one laboratory, the steel consumption is at least tens of millions of tons, and various types of special steel are only one kind of building material for this massive research facility. The other required equipment and materials are even more extensive. Such a large-scale research facility was something Chen Yu wouldn't dare to construct easily. Even if there were spare computational resources, the lack of resources was a significant limitation. However, for Chen Yu, who has fully developed the Jupiter system, this issue is no longer a concern. With the deployment of over 10,000 nuclear fusion ion propulsion spacecraft, his resource acquisition capability has increased more than tenfold. This is his confidence. In addition to the materials science laboratory, Chen Yu has also built equally enormous optical experiment centers, chemical research bases, propulsion technology research institutes, semiconductor technology research bases, power laboratories, metallurgical industry laboratories, mechanical research institutes, aerospace laboratories, large hadron colliders, large particle colliders, high-precision gravitational wave telescopes, large neutrino telescopes, large dark matter detectors, radio astronomy telescope arrays, and many more, totaling 41 categories, comprising over 5,000 super-large scientific research centers. Chen Yu confidently asserts that any one of these over 5,000 super-large research centers, during the peak of human civilization, would require the entire civilization to collaborate for over 10 years to complete. Yet at this moment, Chen Yu is advancing simultaneously, constructing all these over 5,000 super-large research centers. He is well aware that the immense industrial foundation he has built can only be considered a foundation. Although he has expended tremendous effort and invested significant resources and time to perfect his industrial base, these are merely means and tools, not the ultimate goal. These research centers are his true objective. The vast industrial foundation ultimately serves to nurture these research centers. Everything is dedicated to this purpose because only these institutions can generate sufficient scientific data to propel Chen Yu's technological development. After hundreds of years of hard work, exhaustive efforts, and relentless toil, Chun Yu finally possesses the capability to construct such numerous and colossal research facilities according to his initial vision. This is the moment of true harvest. The over 5,000 research centers are now tirelessly engaged in the study of the latest technologies, producing vast amounts of scientific data every day, every hour, every minute, and every second. Under Chun Yu's control, thousands of secondary supercomputers are fully dedicated to analyzing this scientific data. Chun Yu, much like a human scientist, utilized them and harnessed their power to transform the vast and complex sea of data into principles, laws, models, and parameters that he could comprehend and apply. Each piece of research data refreshed Chun Yu's knowledge and deepened his understanding of the fundamental nature of the universe. His scientific development had truly entered a phase of rapid advancement. At this moment, Chun Yu could confidently state that, apart from a few fields where he still lagged behind the peak of human civilization, he had already surpassed human civilization in most areas. This was the boost provided by the nuclear fission ion propulsion spacecraft. As time flew by, under Chun Yu's dedicated research, chip technology finally made another breakthrough. The 2-nanometer chip process successfully passed procedural validation in the laboratory. This meant that, at least theoretically, Chun Yu had mastered the technology for large-scale manufacturing of 2-nanometer chips. The next step was industrial application. Regarding this fundamental technology, Chun Yu unreservedly allocated all available computing power and began constructing a chip factory at the fastest speed. The new chip factory covered an area of 36 square kilometers and was divided into hundreds of zones, encompassing every process involved in chip manufacturing. The construction of the factory took a year, followed by 2 years of testing and adjustments. Chun Yu meticulously examined every step of his manufacturing process, searching for every error and oversight in practical applications, constantly refining his technological implementation plans. On 2 occasions, due to significant issues that could affect final production efficiency and yield, he had to painfully dismantle a third of the massive factory and replace it with newly adjusted equipment. This was time-consuming and troublesome, but it was a necessary process. It was both an adjustment and a learning experience that could not be replaced by other research methods. After all, many hidden problems would not surface in an experimental environment. They could only be revealed in large-scale industrial production. Thus, starting from the grasp of the technology in the laboratory, Chun Yu spent a full 3 years before welcoming the official production of this factory. Advanced chips produced using the 2-nanometer process flowed out continuously, initially replacing the computing equipment used by large factories. Even though Chun Yu conducted countless inspections and adjustments before the final production, numerous issues still surfaced during the year of large-scale practical use. This is the nature of industrial production. Chun Yu was not surprised by this at all. When problems arose, adjustments and improvements were the solution. What stable product has not gone through such a process? Without tens of thousands of minor tweaks and major revisions, could a product stabilize? Chun Yu felt no impatience. Instead, he immediately immersed himself in product improvement. Once it stabilized, Chun Yu began to update and iterate the supercomputers at those large research centers. The importance of these supercomputers goes without saying. It can even be said that aside from Chun Yu himself, these supercomputers are the most crucial. Without a certain level of confidence, Chun Yu wouldn't dare to tamper with them casually. After 2 years of verification and fine-tuning thousands of parameters on these supercomputers, Chun Yu felt that this 2-nanometer chip production line had finally matured and stabilized. This meant that it was time for him to move once again. Chapter 48. Bottleneck. The supercomputer that was about to become his new home was constructed with as much redundancy and backup as possible, employing all means to enhance safety. The construction took a full year, followed by another year for safety verification. After 2 years, Chun Yu finally felt assured about its reliability. Upon moving to this new supercomputer and experiencing its even more powerful computing capabilities, Chun Yu felt invigorated. Compared to the old supercomputer, the new one had increased its computing power by 7 times. At this point, Chun Yu realized that the nuclear fission ion propulsion spacecraft was becoming somewhat inadequate for him. Managing the development of dozens of celestial bodies in the entire Jupiter system consumed less than 10 units of computing power, including the research bases. The maximum computing power used could reach 20 units. What to do with the remaining computing power? There was no place to use it. Building more industrial infrastructure? Impossible, as nearly every exploitable celestial body had already been developed. Building more research bases? Again, impossible, because the resource supply from the dozens of moons in the Jupiter system could only support the current research bases. Any additional bases would lead to a shortage of resources and energy. Conducting scientific research? Promoting scientific development? Not feasible. Without enough research bases to generate scientific data, how could he promote scientific advancement? Mere imagination wouldn't suffice. After evaluating the development levels of every category he was currently involved in, he quickly pinpointed his biggest shortcoming: space transportation capacity. With the increased computing power, he could certainly operate more spacecraft, but the transportation demand within the Jupiter system was limited. Currently, there was no need for so many spacecraft. However, the transportation capacity for celestial bodies beyond Jupiter was still far from sufficient. Even increasing the number of spacecraft several times would not be enough. At present, aside from the celestial bodies within the Jupiter system, the nearest planet with significant development potential was Mars. Mars was a bona fide large planet, its size incomparable to the smaller moons of Jupiter. It could provide more resources and energy, opening up a larger world for him. But it was too far away. When Mars was closest to Jupiter, it was still nearly 500 million kilometers away, and at its furthest, about 900 million kilometers. Such a long distance could certainly be reached by the nuclear fission-powered ion propulsion spacecraft he could currently build. However, large-scale transportation is still far from feasible. The plan to relocate from the Jupiter system to Mars is not viable. While relocation is possible, the abundant and diverse resources in the Jupiter system, along with the industrial foundation built over many years, are indispensable. Both the Jupiter system and Mars are desired by Chunyu. Neither can be missed. Therefore, he must find a way to connect the two. What is the link? Naturally, it is space transportation capability. The key to enhancing space transportation capacity lies in improving the performance of spacecraft. This improvement hinges on two aspects. First, increasing energy density. Second, increasing energy efficiency. The latter seems unlikely to be achievable in the short term. His current ion propulsion technology is nearly at its limit. Without breakthroughs in fundamental theory, further enhancements seem impossible. Thus, he can only focus on energy density. Alas, nuclear fission is still inadequate. Nuclear fusion is essential. After going in circles, he ultimately returned to the starting point. Chunyu attempted to circumvent the limitations of controllable nuclear fusion to achieve the goal of connecting the Jupiter system with Mars using current technology. However, he ultimately realized that this was impossible. The essence of ion propulsion technology is still to drive spacecraft through reaction thrust. It simply achieves superior performance and more efficient propellant usage by ejecting high-speed jets. Currently, the ion thruster he has built can achieve a jet speed of up to 200 kilometers per second. Clearly, the higher the jet speed, the greater the thrust provided by a given weight of propellant. However, increasing this speed is not easy. It involves an overall enhancement of extremely complex ion acceleration technologies. At the current technological level, achieving 200 kilometers per second is the most economical. To raise the speed to 220 kilometers per second, an increase of just 10. Energy consumption rises sharply by around 50. Doubling the speed to 400 kilometers per second would increase energy consumption sixfold. With Chunyu's current ion propulsion technology, this energy consumption cannot be reduced for now. However, the energy supply from nuclear fission reactors has its limits. Excessive energy waste significantly reduces overall acceleration capability. Nuclear fuel that could last a year might be used up in just 1 month. Nuclear fission requires heavy elements like uranium or plutonium, which are scarce and difficult to concentrate, making them unaffordable for Chunyu. This results in a ceiling for space transportation capability, preventing further enhancement. With energy consumption temporarily unable to decrease, the only option is to increase the total energy supply to achieve higher jet speeds. With a larger energy supply, even if not operating economically, a little waste becomes acceptable. Research into controllable nuclear fusion must commence. Only controllable nuclear fusion can significantly enhance the total energy supply. Moreover, while nuclear fission fuel is scarce, nuclear fusion fuel is abundant and easily obtainable. Chunyu made up his mind. In terms of space warfare, only fusion-powered spacecraft have the qualifications. Fission-powered spacecraft stand no chance. Only by mastering nuclear fusion technology can I truly possess the power for self-preservation. Chunyu never forgot the war that took place 20 light-years away. Although 20 light-years is a considerable distance in the vast scale of the universe, it feels as close as the front yard to the backyard. If things go awry, one can never know when that war might spill over to this side. Nuclear fusion releases energy at an average rate about 6 times higher than nuclear fission. Furthermore, after mastering nuclear fusion technology, my energy conversion technology can achieve lower losses compared to fission. Overall, a nuclear fusion reactor could potentially increase the total energy supply by up to 10 times compared to a nuclear fission reactor. With a 10-fold increase, connecting the Jupiter system to Mars would become a trivial task. Moreover, the immense potential of nuclear fusion technology in space warfare makes it imperative for Chunyu to give it the utmost importance. Given various factors, even though Chunyu feels that his technical and scientific reserves are still lacking, he has no choice but to forcefully proceed. Chapter 49. Potato Sun nuclear fusion had already been extensively researched during human times. Back then, there was a famous joke about a person asking a scientist how long it would take to achieve controllable nuclear fusion. The scientist replied, 50 years. Then, 20 years later. The same person asked the scientist again how much longer it would take. The scientist still answered, 50 years. This continued for another 20 years. And each time the person asked, the scientist would respond with the same answer. Thus, the joke of 50 years became eternal, implying that controllable nuclear fusion would always be 50 years away from realization. This joke was, of course, used to poke fun at the prolonged timeline for the large-scale application of controllable nuclear fusion, and it also reflects the difficulties associated with the technology. It is important to note that the controllable nuclear fusion referred to here should mean commercially viable controllable nuclear fusion, rather than controllable nuclear fusion in an absolute sense. In laboratories, controllable nuclear fusion technology has actually already been achieved. Fusion fuel, under human control, releases the energy contained within it gradually. However, the crucial point is that the device used to drive the nuclear fuel to achieve fusion consumes 400 units of energy, while the energy produced from the fusion of the nuclear fuel yields only 1 unit. Currently, there are 2 directions in human exploration of controllable nuclear fusion: magnetic confinement devices and inertial confinement devices. Confinement is necessary because the temperature of the nuclear fuel must be raised to over 100 million degrees for fusion to commence, and clearly, no material can withstand such high temperatures. Therefore, non-contact confinement methods must be employed. Magnetic confinement devices utilize principles similar to magnetic levitation to control the position of the nuclear fuel without direct contact. Inertial confinement devices use principles similar to archery to confine a container that will launch fusion fuel pellets. Before these pellets land, and while they are still airborne, lasers are quickly used to heat them, raising their temperature to over 100 million degrees Celsius, causing them to undergo fusion and release energy. By the time they land, the fusion process has already concluded, and the temperature has dropped, preventing any damage to the mechanical structure. This is the essence of an inertial confinement device. Until the demise of human civilization, there were gains in both directions, but no one knew which route was correct. Of course, Chinyu did not know either. Since there was uncertainty, he decided to pursue both paths simultaneously. Resolutely, he built 2 nuclear fusion research bases, one focused on magnetic confinement and the other on inertial confinement. The research base for magnetic confinement was relatively manageable, occupying only 16 square kilometers, with 2 nuclear fission power plants built to supply energy. However, the research base for inertial confinement was quite extraordinary, currently in the theoretical validation phase and not considering practical applications. Chinyu constructed a vacuum reaction chamber measuring a full 23 kilometers in length to provide more airtime for nuclear fuel, along with 10 power plants. After 3 months of construction and another 3 months of debugging, research officially began. Like humanity, Chinyu initially focused on deuterium-tritium fusion. Hydrogen has 3 naturally occurring isotopes: protium, deuterium, and tritium. Protium, commonly referred to as hydrogen, consists of 1 proton and 1 electron, with no neutrons. The primary constituents of celestial bodies like the Sun, Jupiter, and Saturn are protium. The Sun, as a star, emits light and heat through nuclear fusion, which primarily involves the fusion of protium. Despite its abundance in the universe, using protium for controlled nuclear fusion research is challenging due to the high difficulty of achieving sufficient energy. The energy density of protium fusion is quite low. For example, while the Sun is massive and illuminates the entire solar system, its energy density is unimaginably low. To illustrate, consider that potatoes, commonly consumed by humans, possess a self-respiration mechanism, meaning they can generate heat, but this heat is typically imperceptible because it is too low. Now, if we hypothetically placed a potato the size of the Sun in the same position as the Sun, assuming it wouldn't collapse under its own gravity and would retain its shape, this potato sun would shine dozens of times brighter than the real Sun and could scorch the entire Earth. This demonstrates just how low the power of protium fusion is within the Sun. To increase fusion power, achieving temperatures and pressures several times that of the Sun's core would be necessary, which would result in high-power protium fusion. However, this remains unattainable compared to other methods. Deuterium-tritium fusion is relatively simpler, as it can achieve high power at lower temperatures. Currently, only deuterium-tritium fusion has the potential for commercial application at this technological level. Thus, Chinyu embarked on the arduous research and advancement once again. He had a premonition that this would be a more challenging endeavor than his earlier work on the miniaturization of nuclear fission devices and ion propulsion technology. This is because there are numerous issues to be resolved, such as confinement of high-temperature plasma, device stability, equipment reliability, neutron shielding technology, thermal conversion technology, and many more, each of which could become a bottleneck. If one bottleneck cannot be bypassed, it means that the entire pathway is rendered ineffective. Under such circumstances, Chinyu persevered. However, he had a favorable condition compared to human civilization. he could fully dedicate the industrial and research capabilities equivalent to an entire civilization to this research without internal conflict, misunderstandings, or the need for communication. The ineffective loss was extremely low, with a utilization rate that could exceed 95. In contrast, even when human civilization pooled all its resources and efforts, achieving a utilization rate of just over 10 would be considered exceptional. By this measure, Chunyu was effectively utilizing the equivalent of 10 civilizations' worth of power to tackle the challenges of controllable nuclear fusion technology. In the era of Earth, a pioneering scientist in controllable nuclear fusion once famously stated, "Controllable nuclear fusion will be realized when the whole society needs it." Now, with the power of 10 civilizations pushing its progress and an urgent desire for its realization, this statement resonates strongly. Chapter 50. Tritium Self-Sustainability. In the 10th year of Chunyu's dedicated research on controllable nuclear fusion, after re-optimizing and adjusting the magnetic confinement fusion route, he finally received a somewhat uplifting report. This time, the energy input was set at 100 and the output energy reached 100.02 for the first time, exceeding the input energy. In technical terms, the Q value finally surpassed 1. The Q value refers to the ratio of output energy to input energy, and this undoubtedly marks a significant breakthrough. Compared to the magnetic confinement route, although the inertial confinement route had also undergone a decade of iteration and research by Chunyu, its highest Q value only reached 0.06, which is a substantial gap. The inertial confinement route appears to have little promise. Chunyu pondered, should he simply abandon it? Well, perhaps he should continue. After all, the computational power is idle anyway. There might still be some value in the inertial confinement route in the future. This situation is indeed possible. Just like Riemannian geometry, which was initially developed to describe curved spaces, when it first emerged, no one believed in its value. It wasn't until many years later that it demonstrated irreplaceable value in numerous cutting-edge physical theories, becoming one of the most important mathematical tools. At this moment, Chunyu holds a certain attitude towards the inertial confinement route. Let us keep it. Who knows when it might come in handy? Who can predict the future development of technology? The key point of the inertial confinement route lies in the laser generator. Currently, I can only improve the energy conversion rate of the laser generator to 100 degrees of electricity to produce laser energy, wasting 99 degrees of electricity, with only 1 degree converted into laser energy. Moreover, the reliability of the laser generator is too low. It can only withstand a few hundred impacts on fusion fuel pellets before breaking down, necessitating component replacement, which is quite impractical. In Chunyu's view, the energy conversion efficiency of the laser generator needs to be improved to at least around 50. And its reliability should reach an average of 100 million uses before failure to be considered somewhat promising. Currently, this goal is clearly unattainable. I'll just improve it bit by bit. Chunyu thought humorously. I just remembered that a laser cannon works on this principle. Let us continue the research, treating it as if I'm studying a laser cannon. After all, a laser cannon is just a larger version of a laser generator. Thus, Chunyu continued to push forward with both routes simultaneously. In the 20th year, he made significant breakthroughs in the lithium alloy materials he was researching. Lithium alloy materials have major significance in neutron shielding and tritium self-sustainability. Tritium self-sustainability refers to the need for a nuclear fusion reactor to produce tritium on its own to participate in and maintain fusion. In deuterium-tritium fusion, deuterium is abundant. Although not as much as hydrogen, it is relatively easy to obtain. For example, Jupiter contains about 0.002 deuterium, which can be considered virtually infinite for Chunyu given Jupiter's size. Tritium, however, is different. Due to its short half-life of just a few years, it is almost non-existent in nature. Manufacturing it is extremely difficult. Even with Chunyu's industrial capabilities, producing it would require an enormous amount of energy, potentially driving the Q value below 1, rendering controlled nuclear fusion meaningless. Even if it were produced at any cost, it would be impossible to store it. It would decay before being stored for several decades. Coincidentally, tritium can be generated by bombarding lithium with neutrons. Additionally, up to 70% of the energy produced in deuterium-tritium fusion is released in the form of fast neutrons. This aligns perfectly. I can directly use lithium alloy to construct the walls of the magnetic confinement fusion device, right? This way, the fusion of deuterium and tritium releases a large number of high-energy fast neutrons, which bombard the lithium alloy walls to generate tritium. And the tritium returns to participate in deuterium-tritium fusion to continue generating neutrons, creating a continuous cycle. The theory is promising, but the engineering implementation is extremely challenging. First, the lithium alloy walls must have extremely high heat resistance while also being conductive, allowing heat to be conducted away for power generation. Additionally, the retention rate of tritium must be controlled to prevent too much tritium from remaining in the walls and not participating in deuterium-tritium fusion, which would halt the fusion process. At this moment, Chunyu's material experimental base has finally produced a suitable lithium alloy. After adding a certain trace element and utilizing a special manufacturing method, the lithium alloy he produced completely met the requirements of fusion reactors. This was a breakthrough. The second breakthrough was related to room temperature superconducting materials. Previously, superconducting materials could only operate at extremely low temperatures. After decades of research, he finally found a special material that primarily consists of hydrogen, with added gases like neon and oxygen, manufactured under a pressure of up to 6 million times that of Earth's atmosphere, resulting in a solid substance with metallic properties. This material exhibited superconducting capabilities at temperatures not exceeding 63 degrees Celsius, fully meeting his requirements. Another 10 years passed, and he completed small-scale trials of these two materials. At the Magnetic Confinement Laboratory, the Q value of the nuclear fusion device reached 26 for the first time, with an ignition time of 3 hours. After replacing these two materials, the performance of the fusion reactor surged, with the Q value increasing to 75 and the ignition time extending to a month. An ignition time of a month refers to the process where neutrons bombard lithium to produce tritium, which participates in fusion to generate neutrons, and the cycle continues, lasting a full month before being halted due to insufficient tritium production. Although this had not yet met the requirements for industrial and commercial applications, it was already a significant advancement. He continued to invest substantial computational power and resources into relentless research. In the 50th year, there was a major breakthrough in fundamental physics research, particularly in plasma physics. He comprehensively improved the plasma steady-state control device of the nuclear fusion reactor, greatly enhancing its stability. As a result, the Q value increased to 106, and the ignition time reached 6 months. From this point onward, he began attempting to construct a nuclear fusion power station. By the 60th year, the first nuclear fusion power station with practical value was completed and began grid-connected power generation. Simultaneously, research on the miniaturization of fusion reactors was initiated. This power station was experimental and would operate for a long time. The data generated during its operation would serve as the foundation for further optimizing nuclear fusion power generation. Thus, he focused on 4 research directions: improving Q value, extending ignition time, enhancing overall installed capacity, and miniaturizing fusion reactors, and began concurrent studies in these areas. Chapter 51. Nuclear Fusion Spaceship. The significance of improving the Q value is self-evident, as it is the basis for the energy output of fusion reactors. In this regard, he explored research through various aspects, including reducing energy consumption, enhancing control precision, improving the completeness of fusion, and increasing equipment accuracy. Each aspect involved dozens to hundreds of research projects, with each project being conducted by one or more specialized research institutions. This single research direction entailed hundreds of large research institutions, which in turn involved more upstream mechanical factories, power plants, foundries, metallurgical plants, chip manufacturers, transportation networks, and so on. Such a massive project, if it were to be undertaken by human civilization instead of a model like Chunyu's, would likely incur significantly higher losses. Research on extending ignition time is equally important, as it pertains to the stability of nuclear fusion reactors. Chunyu certainly does not wish for a day when a spacecraft he is aboard suddenly extinguishes its fusion reaction and can no longer reignite. Within a star system, it is somewhat manageable since supplies can be relatively easily obtained. However, in the interstellar space beyond a star system, there may not be any macro material within several light years, which would truly be a situation of no help from either the heavens or the Earth, leaving one with no options. This aspect can be improved primarily through more advanced lithium alloy materials, tritium self-sustaining technology, and plasma stability research, which also involves numerous research institutions. The overall installed capacity relates to the scale of the reactor. It is evident that larger spacecraft require higher overall capacity. As for miniaturization, there is no need to elaborate. For instance, the nuclear fusion power station Xinyu is currently constructing occupies several million square meters, making it impossible for any spacecraft to provide such space. These 4 research directions involve various aspects of Chunyu's technological system. He must integrate the entire scientific framework, advancing together in synchronization to ultimately promote research progress. Utilizing all satellites of significant size in the Jupiter system as resource sources, Chunyu is doing his utmost to push the heavy vehicle of science forward slowly. As time passes, in the 70th year of the research, the second nuclear fusion power station with practical value goes into operation and begins to connect to the grid. Compared to the first nuclear fusion power station, its footprint is half the size, yet its energy output is 10 times higher, and its energy consumption has dropped to 1/3 of the original. At the current stage, nuclear fusion power stations do not have any advantages over nuclear fission power stations. Their overall efficiency is roughly on par with that of conventional thermal power stations. However, The upper limit of thermal power stations is fixed, no matter how advanced the technology. It cannot surpass that limit. Although the current level of fusion power stations is comparable, their potential is unknown, possibly millions of times higher. After another 20 years of development, despite the unknown number of spacecraft that may have malfunctioned, the amount of mineral resources consumed, and the numerous iterations, the overall efficiency of the nuclear fusion power station finally matches that of the nuclear fission power station. At this moment, Qinyu's advancements in Q-value enhancement, overall installed capacity, reactor miniaturization, and ignition time length have all made significant progress. The latest developed controllable nuclear fusion ship reactor has achieved performance indicators that are now comparable to the mature nuclear fission reactor in terms of size, mass, and stability. This means that Xunyu can completely retrofit the current nuclear fission spacecraft into nuclear fusion spacecraft without any loss in performance. However, this is still not enough. Merely matching the performance holds no significance for Xunyu. What he seeks is higher energy density, longer range, and greater acceleration capabilities. At this moment, Xunyu can confidently declare that he has completely mastered controllable nuclear fusion technology, albeit to a lesser degree. As time slowly passes, over a decade has gone by in the blink of an eye. On this day, Xunyu finally achieved a goal he had never dared to imagine before. In the nuclear fusion reactor, the tritium produced from the bombardment of lithium alloys by fast neutrons has, for the first time in history, exceeded the amount of tritium consumed in the fusion process. Prior to this, the most advanced nuclear fusion reactor built by Xunyu had been operating continuously for 16 years without a shutdown, and it is expected to run for at least another 10 years. However, even if it could operate for 30 years continuously, there would still be time limitations. Once the fusion reactor shuts down, it would need to replenish tritium to reignite. But now, with the output surpassing consumption, it means that the limitation on the duration of tritium self-sustenance has been completely overcome by Xunyu. From now on, as long as the equipment remains undamaged, nuclear fusion can continue indefinitely without the worry of shutdowns. This significant breakthrough greatly invigorated Xunyu. Since then, his luck seemed to have turned for the better, with a series of major issues being resolved in just 5 years. Could this be the result of accumulated experience yielding explosive breakthroughs? After years of research spanning over 100 years at thousands of large-scale integrated research bases, the scientific data finally underwent a qualitative change due to quantitative accumulation. Xunyu felt a sense of pride, as all of this was achieved under his persistent efforts. The resolution of these major issues allowed the total energy output of the fusion reactor per unit weight and volume to reach 5 times that of a fission reactor for the first time. Yet, this is still not the limit. Xunyu has a premonition that in no more than 20 years, this figure will reach around 12 times. In an ideal scenario, the energy produced from nuclear fusion using the same mass of fuel is about 5 times that of nuclear fission. However, the conversion of fission reactor energy into usable electrical energy involves significant losses. The newly developed system by Xunyu, specifically designed for converting energy from nuclear fusion reactors, can minimize these losses. This is how the energy from nuclear fusion can exceed that of nuclear fission by 12 times. Although it has not yet been developed to its full potential, the time to construct fusion-powered spacecraft has now arrived. It was time for a change. Xunyu made this immensely significant decision for himself. He did not directly modify the existing fission-powered spacecraft, because those were specifically designed for fission power and were not suitable for fusion. Instead, he developed an entirely new spacecraft, which, after several years of iterations and improvements, was finally finalized and produced. With a completely new structural layout, new materials, a new power source, and significantly upgraded ion propulsion systems, communication systems, radiation protection systems, heat insulation systems, and electrical control systems. This fusion spacecraft's overall performance exceeded that of the original fission spacecraft by more than 10 times. Chapter 52, Jupiter Aircraft. At this moment, the brand new cargo spacecraft, with a total mass of 2,000 tons and a maximum internal load of 6,000 tons, was soaring freely in the vastness of space under Qinyu's control. Looking at the spacecraft, Xunyu felt a surge of pride and satisfaction. Then there's nothing more to say. Let us start mass production. First, connect the Jupiter system with Mars, allowing me to supply a greater number of large research bases. As for the spacecraft's performance and further enhancement of controllable nuclear fusion technology, those can proceed simultaneously. Once we achieve a significant breakthrough next time, we can carry out an overall transformation and upgrade. As a result, the original nuclear fission-powered spacecraft production line was dismantled, with all building materials being recycled. Anything that couldn't be recycled was discarded. The new nuclear fusion-powered spacecraft production line would occupy about 126 square kilometers. Even with Chunyu's engineering capabilities, it was estimated that it would take more than 5 years to construct. During these 5 years, Xunyu also planned to undertake another extremely important construction task, a deuterium-tritium refining base. The two fusion fuels, deuterium and tritium, were scarce on Jupiter's moons. Deuterium was somewhat better, with a concentration of about 0.0006 in the oceans of the Galilean moons, allowing for some collection through large-scale seawater filtration. Tritium, however, was a complete lost cause. This substance could only be formed naturally through cosmic high-energy radiation, and it would decay itself in just a few years, with its natural concentration in seawater being far less than 1/1,000,000th. Relying on seawater filtration to collect tritium was simply not feasible. However, tritium was a one-time investment. Once produced, it would not be needed again. But even for deuterium, the efficiency of collecting it through seawater filtration was far too low. Once the nuclear fusion spacecraft were mass-produced, the enormous amount of fusion fuel required could not realistically be sourced this way. The only viable solution was to collect it from within Jupiter itself. According to Chunyu's observations, in Jupiter's atmosphere, hydrogen, or protium, accounted for over 75, helium about 24, and deuterium around 0.02. This made it very suitable for large-scale extraction. Then, let us advance towards Jupiter. Chunyu resolved. Due to Jupiter's harsh environment, with intense radiation and strong magnetic fields, coupled with the absence of irreplaceable resources on the planet, Chunyu had previously only conducted remote observations and had not engaged in any significant activities on Jupiter. However, now, with the sudden increase in demand for deuterium and advancements in technology that allowed Chunyu's mechanical creations to survive in Jupiter's atmosphere, the conditions for advancing towards Jupiter were finally ripe. After a period of preparation, a fleet of 100 specially designed spacecraft, carrying robots and related machinery tailored for Jupiter, departed from one of its moons, heading towards the massive planet ahead. As they drew closer, Jupiter gradually expanded, eventually filling the entire view ahead. At this moment, even with the naked eye, one can clearly see the intertwining air currents, the unimaginable violent winds, and thunderstorms within the atmosphere of the gas giant. There are indeed thunderstorms inside, with an intensity far beyond anything on Earth. The most intense thunderstorms on our planet would seem like a mere tickle compared to those on this giant. Here, a single lightning bolt can stretch for hundreds of kilometers, releasing energy hundreds of times greater than that of earthly lightning, a common occurrence. The winds here are also extremely fierce, easily reaching speeds of 100 meters per second, equivalent to a force 17 gale on Earth. The most intense typhoons on our planet would seem like quiet kittens in comparison. In some of the most hostile environments, even the most advanced spacecraft manufactured by Chunyu would struggle to withstand the conditions. Fortunately, Chunyu does not need to venture into those areas. At this moment, Chunyu's destination is the surface of the giant. Of course, this planet does not have a solid surface. It is a gas giant composed entirely of gas. However, for research purposes, much like scientists on Earth, Chunyu refers to the region of the atmosphere where the pressure equals that of the Earth's surface as the surface of the giant. In this region, while storms and thunderstorms can still be quite violent, they are somewhat less intense than those found deeper within, at a level that Chunyu can just about endure. Currently, Chunyu's fleet is navigating through the fierce storms, enduring significant radiation and magnetic field interference, and has finally arrived here. This place is truly uninhabitable. Feeling the ferocity of the giant, Chunyu silently laments. At this moment, hail the size of soccer balls is falling, crashing down at speeds of several tens of meters per second, making the outer hull of the spacecraft crackle. Fortunately, these spacecraft are specially designed. Otherwise, this hailstorm could easily destroy them. Above the spacecraft is a sky that is dark yet not entirely black, with a faint yellow hue piercing through the darkness. Heavy and oppressive, obscuring any stars. Below lies a bottomless abyss of gas, seemingly extending down into hell, giving an unsettling chill to anyone who gazes into it. The violent lightning branches out like a tree in the dark sky, each bolt illuminating the entire area in an instant, only to extinguish moments later, followed by the deafening roar of thunder. When there is neither lightning nor thunder, the fierce winds produce sounds reminiscent of wailing ghosts, sending shivers down one's spine. Fortunately, Chunyu is well experienced and not easily disturbed by this hellish scene. If human astronauts were to come here, it would not be surprising if they were driven to madness. In this situation, Chunyu began his construction. He aims to build a large aircraft powered by nuclear fusion here. This aircraft measures over 200 meters in length, 50 meters in width, and about 22 meters in thickness. Its overall shape is butterfly-like, thick in the middle and thin on the sides. While spacecraft do not need to adhere to aerodynamic principles due to the absence of air in space, this is not the case inside the giant, where gas surrounds everything. Through his research, Chunyu has determined that this particular shape is most suitable for maintaining stability within the giant's atmosphere. The aircraft, with its butterfly shape, is equipped with a total of 20 high-performance ion thrusters and 6 air jets. enabling it to counteract the gravity here, which is 25 times that of Earth, allowing it to hover and move around easily. Among these, the 20 ion thrusters serve as the main propulsion system, while the 6 air jets act as support. There are also 16 large air intakes on its body. The atmosphere of the gas giant will enter through these intakes and be expelled through the air jets, with the deuterium present being filtered out and stored. Chapter 53. Mars Development in the harsh environment of the gas giant. Yu spent a full month constructing this aircraft, which is unusual for someone with such formidable engineering capabilities. To put it into perspective, even building a factory 10 times larger than this aircraft on one of the moons of the gas giant would take no more than 10 days. The environment here is simply too severe. During this month, one spacecraft was directly damaged and plunged into the depths of the gas giant, leaving no trace. In addition, there were as many as 109 mechanical failure incidents, and over 500 robots were blown away, leaving Yu for good. Fortunately, although it was challenging, the aircraft was finally completed. The newly constructed aircraft can intake up to 15 tons of the gas giant's atmosphere per second, filtering and expelling it. Based on the local deuterium concentration of approximately 0.002, it can filter out about 3 kilograms of deuterium, totaling around 260 tons per day. At this stage, 260 tons of deuterium is enough for Yu's needs. Therefore, one aircraft is sufficient for the current phase. However, to enhance stability and prevent accidental damage, Yu plans to build 2 more aircraft to operate simultaneously, making a total of 3. Currently, this is the first aircraft. It has now been debugged and is ready to begin operations. Yu issued a remote command, "Start up." After a delay of about 2 seconds, he received feedback on his command, which left him momentarily stunned. To his surprise, the weather warning system reported that a hurricane was about to form, a phenomenon that on Earth would be considered a mild breeze. But here it was a genuine hurricane of the gas giant, and it was forming very close to the aircraft. Without hesitation, Yu ordered an immediate retreat. They needed to leave this place quickly. However, just a few kilometers into their flight, a massive force suddenly emerged from above the aircraft, pressing down heavily. The automatic control system immediately increased the thrust power of the ion thrusters in an attempt to maintain stability. But the force was too great, even at maximum power. The system could not counter it. Facing the risk of destruction, the control system disregarded the potential damage to the ion thrusters and decisively increased the thrust again, which it had the authority to do. The blue tail flame of the ion thrusters became intensely bright and hot in an instant. The next moment, the ion thrusters exploded. The Jupiter aircraft, which Yu had painstakingly assembled, suddenly lost power and began to roll into the unfathomable depths of Jupiter, severing its connection with Yu in an instant. Yu felt an overwhelming surge of frustration. How could this be due to wind shear? Such bad luck. Wind shear is a meteorological phenomenon where wind direction changes abruptly, posing a significant threat to aircraft. This phenomenon exists on Earth, and naturally, it also occurs on Jupiter. Once it takes effect, its impact is even greater than on Earth. This setback rendered a month's worth of Yu's hard work futile. Jupiter is simply too unstable. After the initial anger, Yu reluctantly accepted the situation. Just like the infamous Great Red Spot, a massive storm capable of containing 3 Earths, it had been raging on Jupiter for centuries and was still intact. Recently, it seemed to be intensifying. Who could he turn to for answers? Unable to change Jupiter, he could only change himself. Yu realized he had somewhat underestimated Jupiter's volatility. There was no choice but to redesign and enhance the stability of the Jupiter aircraft. This time, Yu spent 6 days reworking the design plans, half a month on production, and another month and a half assembling it within Jupiter. Finally, he completed its construction. This time, with enhanced meteorological warnings, Yu chose a calm and sunny location for the Jupiter aircraft. Well, even though this place was sunny, the sky was still overcast with no visible celestial bodies. Heavy clouds of hydrogen sulfide floated above, and wind speeds still reached 50 meters per second, equivalent to a force 10 gale on Earth. But this was the best meteorological environment he could hope for. He couldn't ask for more. Under these conditions, the Jupiter aircraft finally commenced operation. With the air ejector in action, the already high-speed Jupiter atmosphere was rapidly drawn into the aircraft, then diverted to different processing workshops. Here, a series of separation procedures were carried out step by step. All gases except deuterium and tritium were ultimately mixed together and expelled. The Jupiter atmosphere contains trace amounts of tritium. Since air separation was to be performed, Yu added this step as well. The Jupiter aircraft could separate about 260 tons of deuterium gas daily, but only around 0.1 grams of tritium, which was hardly significant. After 10 days of continuous operation, a specially designed spacecraft capable of flying within Jupiter's atmosphere arrived to transport the accumulated 600 tons of deuterium and 1 gram of tritium away. In space, The hundreds of fusion-powered spacecraft that Chen Yu had built were eagerly awaiting their supply. With sufficient energy now available, these spacecraft were finally ready to embark on their journey. Their ultimate destination would be Mars, currently a staggering 6.8 billion kilometers away, to deliver mechanical equipment and energy totaling over 100,000 tons. Yes, at this moment, Chen Yu was finally set to initiate the grand development of Mars. As early as the era of nuclear fission spacecraft, Chen Yu frequently dispatched ships to reach Mars, conducting detailed explorations and subsequent development planning for the planet. However, due to insufficient transport capacity, large-scale development had not yet occurred. Now, with the advent of nuclear fusion spacecraft, this work can finally begin in earnest. At this moment, Chen Yu is filled with ambition. I want to build over 5,000 large nuclear fusion power plants on Mars, construct millions of various factories, create at least 1 billion robots, and ensure that my footprints can be found in every corner of Mars. I aim to have a fleet of at least 100,000 nuclear fusion spacecraft, truly connecting Mars with the Jovian system, allowing both to contribute to my technological advancement with their power and resources. In the future, I will also develop Venus, Mercury, gather minerals from the debris belt of Earth, and develop Saturn, Uranus, and Neptune, using the resources of the entire solar system to support my technological development. In Chen Yu's plan, the Jovian system will become his energy and research center, while Mars is designated as the mineral and industrial center. In the future, Chen Yu will follow this general classification method. Rocky planets such as Earth, Mars, Mercury, and Venus, which are primarily composed of rock and rich in minerals and resources, will serve as mineral and industrial centers. Gas giants like Jupiter, Saturn, Uranus, and Neptune, which are mainly composed of gas and contain abundant nuclear fusion fuel, will be planned as energy and research centers. This way, the two types of planets will complement each other, providing energy, minerals, industry, and research, fulfilling all four aspects. Under the communication and connection of nuclear fusion spacecraft, significant development can be achieved in all four areas. The importance of nuclear fusion spacecraft is evident. Without this crucial bridge, all of Chen Yu's plans would be mere illusions. At this moment, under the transport of just over 100 nuclear fusion-powered spacecraft, the first batch of building materials, machinery, and other equipment has already arrived on Mars. This transport is vastly different from previous minor shipments. This time, a single trip brought in various machinery weighing several 100,000 tons, and the resources sourced locally are sufficient to construct a relatively large industrial base. Thus, a grand construction initiative has begun once again on this planet, several 100 million kilometers away from Chen Yu's control. Faced with a communication delay of over an hour between the two planets, Chen Yu had no choice but to adopt an indirect control model. Data from Mars continuously reaches Jupiter, where Chen Yu processes this information in real time, constantly adjusting future action plans based on past data, allowing the machinery over there to operate roughly according to his vision. This mode of operation is certainly less efficient than direct control by Chen Yu himself. However, without mastering faster-than-light communication technology, this is the only option at this stage. In the midst of a busy schedule, Chen Yu did not forget to accomplish one task. Under his remote manipulation, a massive all-terrain construction vehicle raced across the desolate surface of Mars, eventually arriving at the back of a mountain. Here, a small base was enduring the ravages of a Martian sandstorm. This was a genuine Martian base, but it was not constructed by Chen Yu. Rather, it was built by the earlier human civilization. It was from this location that Chen Yu had initially acquired some supplies, providing him with the capital to start anew. Without the fuel from here, without the 3D printer, and without that pitiful multifunctional mining robot, Chen Yu would have perished long ago. At this moment, it had been several hundred years since Chen Yu took those supplies. Under the relentless erosion of Martian storms, the base had long since fallen into disrepair, with some areas already collapsed and buried by sand and dust. Observing the dilapidated state of the base filled Chen Yu with nostalgia. It felt as though he had just lived and worked in this base as a human. Time had flown by in the blink of an eye, and humanity had long since passed away. Now, he, inheritor of the human bloodline, had risen again in the solar system, reaching heights beyond those of human civilization. At this moment, Chen Yu's technological prowess had completely surpassed that of human civilization. This base, along with the ship he initially boarded, served as perhaps the only link he had with human civilization. I must protect them well, Chen Yu thought silently, controlling the robot to dismantle the base and collect all its building materials. In the future, these items would be stored alongside the ship. Wherever he might go, he would take them with him. I will always remember that I am human, born on Earth. No matter what form I take in the future, I will never forget this. After paying silent tribute to the civilization that had perished, Chen Yu set aside his burdens and officially began the monumental construction task. Iron tracks emerged across the barren Martian landscape, and high-speed trains began to race along them. The skies of Mars were filled with roaring helicopters, versatile spacecraft, and vast bases. A wealth of minerals buried beneath Mars's surface was being extracted, with countless machines roaring day and night. In the blink of an eye, another 10 years had passed. On this day, a standard nuclear fusion spacecraft roared to life from the Martian shipyard, entering the vastness of space. Chen Yu felt a surge of joy as he watched the spacecraft. It was ordinary yet extraordinary. It was ordinary because it was identical to other standard spacecraft in terms of performance specifications, appearance, and core parameters. It was extraordinary because it was the first spacecraft Chen Yu had built beyond the Jupiter system. The Martian shipyard, capable of producing up to 5,000 standard spacecraft annually, had now been completed. Starting today, an average of 13 spacecraft would roll off the production line daily, setting sail into the cosmos. The resource potential of the entire Jupiter system could only support a production line capable of producing 1,000 spacecraft per year. On Mars, the first spaceship factory built by Chen Yu can produce 5,000 ships annually. The scale of a true large planet is so immense that it is incomparable to that of a satellite. To support this massive spaceship factory, Chen Yu constructed tens of thousands of upstream factories and mineral centers. He built over 100 nuclear fusion power stations alone, alongside the large-scale development of Mars. Another noticeable change is that the number of factories in the Jupiter system has begun to gradually decrease, while the number of large research centers has rapidly increased. Breaking free from the constraints of the Jupiter system and with the resource support from Mars, Chen Yu can withstand the construction of even more research centers. The more research centers there are, the faster his technological progress will be. This is the most direct benefit of developing Mars. As time slowly passes, Chen Yu's industrial power has nearly covered the entire Mars, and preliminary development has also begun on Mercury and Venus. In the Jupiter system, the number of large research centers has increased from 5,000 to over 16,000. The number of nuclear fusion transport ships under Chen Yu's control has finally reached 100,000. This is nearly the upper limit he can manage at this stage. Beyond this number, he would find it difficult to operate. The 100,000 ships travel day and night throughout the solar system. At this point, Chen Yu feels that the timing for developing military technology has finally arrived. Chapter 55. 4 types of weapons. Chen Yu had long predicted that controllable nuclear fusion technology is the foundational technology for interstellar warfare. Developing military technology before mastering controllable nuclear fusion is meaningless. Any enemy capable of reaching the solar system must have already mastered interstellar travel technology and controllable nuclear fusion. An enemy equipped with interstellar travel technology cannot be harmed by one's own capabilities based on nuclear fission or chemical energy. Ancient armies clad in armor, riding horses, and wielding bows and swords, no matter how strong the armor, how majestic the horses, or how sharp the weapons, cannot compete with modern armies. Modern militaries would not even appear within the line of sight of ancient forces. A single missile could wipe out thousands of ancient soldiers. If Chen Yu were to develop military technology before mastering nuclear fusion, it would be akin to ancient warriors forging divine weapons in an attempt to confront modern armies. At this moment, the large-scale development of Mars has reached a milestone. The subsequent steps are merely a matter of upgrades and iterations. With the operation of 100,000 ships ensuring resource and energy supply, Chen Yu can now recover a portion of computing power. This computing power is directly invested into the research and development of military technology. Based on my relatively mature understanding of controllable nuclear fusion technology, the weapons in current space interstellar warfare can roughly be divided into 3 categories. First, kinetic energy weapons. Kinetic energy weapons primarily consist of various projectiles and shells. They do not have their own propulsion. Once they leave the launcher, their trajectory is already determined. In the era of interstellar travel, kinetic weapons clearly cannot rely on chemical energy. They should utilize electromagnetic acceleration technology, specifically electromagnetic cannons. However, I can already accelerate projectiles to hundreds of kilometers per second with existing electromagnetic cannon technology, which is sufficient for causing damage. Moreover, the projectiles for electromagnetic cannons are too small. Even if they contain explosives, the energy from the explosion is negligible compared to the kinetic energy, making it unnecessary to complicate matters. Thus, the focus should be on speed, primarily relying on kinetic damage. This is analogous to the Earth era, where one could say that the decision was made to only produce machine guns and not artillery. The second type of weapon is guided weapons. Guided weapons have their own propulsion and can accelerate and change direction after leaving the launch platform. These can collectively be referred to as interstellar missiles. Chemical propulsion is clearly inadequate. Ion propulsion is required. However, ion propulsion consumes too much electricity and batteries won't suffice. A fusion reactor is necessary. Yet, A small missile cannot accommodate a fusion reactor, so perhaps a fission reactor could work? Fission reactors can be made smaller and could fit inside missiles. Additionally, interstellar missiles do not require long-lasting power, but rather a short, high-speed burst, which aligns with the capabilities of fission reactors. Therefore, it is decided that guided weapons will utilize nuclear fission power with ion propulsion. The third type of weapon mainly consists of various beam weapons, such as laser cannons and gamma-ray cannons. The speed of these weapons is at the speed of light, and it is impossible to anticipate or defend against them before mastering faster-than-light technology. These weapons are crucial and should be developed vigorously. The laser technology that I possess has been accumulated from the development of controllable nuclear fusion technology, particularly from the inertial confinement approach. It has been proven that controllable nuclear fusion technology ultimately relies on magnetic confinement. The inertial confinement route is not viable. However, research into inertial confinement has significantly enhanced my laser technology, which is now perfectly suited for creating laser cannons. Additionally, there needs to be a fourth type of weapon, which can be collectively referred to as special weapons. I can easily create trigger-based bombs, disguise them, and scatter them in space. Once an enemy ship is detected passing by, they would automatically activate and explode upon contact. This type of weapon could be called space mines. Alternatively, I could create metal fiber bombs that, upon detonation, release countless fine metal fibers that invade the enemy ship's hull and cause short circuits in their internal wiring. These four types of weapons can also be combined. For example, interstellar missiles could launch special weapons, and electromagnetic cannons could do the same. In short, the forms of interstellar warfare are ever-changing, and I will adapt flexibly. The basic styles of weapons are established. Any technological advancements comparable to mine will likely result in variations of these four types of weapons. Now, I need to consider how to approach defense. If we can master these four types of weapons, the enemy can do the same. When the enemy uses these weapons against us, how should we defend ourselves? To develop military technology, I have specifically constructed 20 large research bases for RD and built 2 supercomputers to conduct war simulations. In addition to hardware such as spacecraft and weapons, software is also crucial. Software refers to aspects like tactics and command. The simulated warfare conducted within this supercomputer serves the dual purpose of hardware development and software enhancement. Chunyu directly multitasks, setting up 2 factions on the simulated battlefield. Each faction is primarily focused on completely annihilating the other, employing extreme measures in warfare. Deception, traps, ambushes, survival strategies, sacrificing pieces to save the whole, long-distance infiltration, nuclear contamination, and electromagnetic storms. Both factions are locked in a relentless struggle. Chunyu exhaustively considers every method to destroy the enemy. Once he devises a strategy, he immediately manipulates the opposing faction to brainstorm defensive and counterattack tactics. After facing a counterattack, he then contemplates ways to resolve the situation, continuously cycling through this process without pause. Under these circumstances, Chunyu's command and decision-making skills in warfare are rapidly improving. Gradually, he learns how to allocate forces between defense and offense in space warfare, how to ensure logistics, how to protect bases, how to deploy formations to minimize attacks while maximizing offensive capability, how to strike at the enemy's rear, how to cut off their supply lines, how to force the enemy into a decisive battle, and how to find breathing space in unfavorable situations. Chunyu is learning and growing swiftly. At this moment, he even feels that his greatest advantage over ordinary intelligent civilizations is not necessarily in technological development, although that is significant, but rather in warfare. The ability to command a vast fleet with precision, make quick and accurate decisions, process data beyond imagination, and learn and iterate at an unprecedented pace. His strategic simulation capabilities surpass those of countless advisors combined. Could it be that I was not born for scientific research, but rather for warfare? Chunyu reflects silently. Chapter 56. Stardust. Once Chunyu felt he had mastered enough theories and tactics of warfare through continuous self-iteration, he shifted his focus to hardware. In the space age, the hardware for interstellar warfare is naturally spacecraft. The reason for this sequential arrangement is that Chunyu understands that only by first grasping how interstellar warfare is conducted can he determine what kind of spacecraft he truly needs. After constructing the spacecraft, practical space exercises can reveal more details of warfare, allowing for continuous adjustments and attempts, thereby enhancing warfare theory. The improvement of warfare theory, in turn, drives the advancement of combat spacecraft, allowing both aspects to develop rapidly in tandem. At this moment, a dedicated production line for combat spacecraft has been established in the orbit of a certain moon. Yes, this time the spacecraft factory is not built on the ground, but in space. The absence of gravity in space allows for a more stable production environment for Chunyu spacecraft. Regular civilian spacecraft do not require such high standards, but combat spacecraft are different. The combat spacecraft must strive for perfection, utilizing the best materials, adhering to the most rigorous processes and quality control, and employing the most advanced technology. After years of continuous research and development, with numerous complete redesigns and hundreds of thousands of experiments and adjustments, Chen Yu finally created the first combat spacecraft of his life. Launch. With Chen Yu's command, a spacecraft with a disc-like structure, entirely painted black, approximately 40 meters in diameter, and about 10 meters thick at its thickest point, slowly left the dock under the propulsion of ion thrusters, entering the vast emptiness of space. Looking at the spacecraft, Chen Yu felt a deep sense of pride. It is a war machine designed for slaughter and combat. He poured all the advanced technologies accumulated over centuries into this vessel, endowing it with the most powerful combat capability achievable under his current technological level. This spacecraft uses a fusion reactor for energy and high-energy ion thrusters for propulsion. Its framework is made of high-performance alloy steel, equipped with thick outer armor. Such resilient materials give it a high overload resistance. At its maximum limit, its acceleration can reach 100 meters per square second, resulting in an overload pressure equivalent to 10 times that of Earth's gravity. Even so, its hull will not deform. The heavy, specially designed multi-layer armor provides exceptional defensive capabilities. In practical tests, its armor can withstand full-force attacks from small electromagnetic cannons. It is important to note that even a small electromagnetic cannon can accelerate a projectile weighing 1 gram to a speed of 300 kilometers per second. Such a projectile would possess about 45 million joules of energy, roughly equivalent to the explosion energy of 10 kilograms of explosives. The coating on the armor's surface also grants it a high stealth capability, at least with the space scanning radar developed at Chen Yu's technological level. Detecting it would be quite challenging. Additionally, this coating has a high reflectivity, meaning it offers significant defensive capabilities against laser weapons. Equipped with 6 space scanning radars and an equal number of optical scanning devices, the spacecraft can continuously observe activities within a radius of 10,000 kilometers in real time, effectively collecting battlefield information to inform decisions for the next phase of combat. Beyond propulsion, defense, and spatial awareness, the most crucial aspect, which Chen Yu values the most, is the combat equipment. In terms of combat equipment, the spacecraft is armed with 8 small electromagnetic cannons, each capable of firing projectiles weighing 1 gram at a rate of 10 rounds per second, reaching a launch speed of 300 kilometers per second. The main cannon is a medium-sized electromagnetic cannon, also firing at a rate of 10 rounds per second, but with a projectile mass increased 6-fold to 6 grams, achieving a launch speed of 400 kilometers per second. In addition to the electromagnetic cannons, it is equipped with 3 laser cannons and 40 small high-speed interstellar missiles. The interstellar missiles are equipped with tactical hydrogen bombs. Once they hit their target, the energy released by the explosion can vaporize even a space station. However, the size of the interstellar missiles limits their maximum speed to about 100 kilometers per second, making them relatively easy to intercept. This restricts their operational scenarios, allowing them to be effective only in specific situations. Nevertheless, once they are deployed, it signifies the end of the battle. This fully armed combat behemoth is the first generation of combat spacecraft developed by Chen Yu. At this moment, a decommissioned spacecraft, acting as a target drone, is fleeing at high speed away from Jupiter. Under Chen Yu's control, the combat spacecraft emits a bright light from its side, propelling it to accelerate at an incredible speed, rapidly chasing after the target drone. With several thousand kilometers still to go, the high-precision automatic targeting system adjusts the electromagnetic cannon's muzzle, locking onto the target accurately. Then, 3 electromagnetic cannons fire simultaneously, sending hundreds of high-speed projectiles rushing forward. Moments later, the target drone erupts in a dazzling flash of light. An interstellar missile swiftly launches, adjusting its trajectory in response to the target drone's evasive maneuvers, like a venomous snake fixated on its prey. Eventually, the missile meets the target drone, and with a brilliant explosion, the tactical hydrogen bomb detonates, engulfing the drone in terrifying high temperatures. When the light dissipates, the target drone has completely vanished, vaporized into interstellar dust, and has dissipated into the void of space. The combat spacecraft and civilian spacecraft are indeed 2 different worlds. Chen Yu reflects, with just one such combat spacecraft and enough time, it could destroy even 100,000 civilian ships. In the future, I will build more advanced and larger combat spacecraft. Chen Yu silently thinks, you are the first combat spacecraft I have created, so I will name you Stardust. Interstellar dust is the most common and fundamental element in the universe. However, it is precisely through the collapse of interstellar dust that bright stars and colorful planets emerge. As the beginning of all Chen Yu's future combat spacecraft, this first-generation battleship has been given a name of special significance, Stardust-class battleship. Chapter 57. fleet core based on different tonnages, combat capabilities, and tactical positioning of the battleships, the smallest ones, directly undertaking frontline combat tasks, are named Stardust-class battleships by Chinyu. The next larger class, which can serve as the flagship of a combat squad, will be named Nebula-class. When interstellar dust gathers together, it is referred to as interstellar dust clouds, abbreviated as nebulae. The ships in the Nebula class will serve as the core of an entire fleet, and Chinyu plans to name them Comet class. Above the Comet class is the Dwarf Planet class, followed by the Satellite class, Planet class, Star Cluster class, Arm class, Galaxy Cluster class, and so on, all the way up to the final Cosmic class. However, given the current military technology level, the highest that can be produced is only ships of the Comet class. Anything larger simply cannot be constructed until military technology develops further. When it comes to warships, bigger is not always better. A sufficiently large warship requires advanced materials technology, propulsion technology, and energy technology